Dear guests, are you hearing me clearly?
Yes.
Thank you very much. My name is Konstantin Usherin. I am chair of this section. I'm glad to see you on our conference, and I encourage you to ask questions, start discussion, and communicate with each other after each presentation. And we glad to see you here. We have 3 minutes to start first presentation. It's presentation of Anvar Kurmukov, fast lung localization in computed tomography by 1D detection networks. It's very interesting topics. We start at 11 o'clock in local time and in 9 a.m. In Moscow time. After only 2 minutes to, are you ready?
Yeah, I'm sorry. So Vladislav Proskurov will make a presentation. He's the first author of the paper. I've just registered the in the conference website.
Perfect.
But Vladislav will do the presentation.
Good morning.
Thank you very much. Could you start share your screen, and you can start. You can start if you want.
Yes. Good morning. My name is Vladislav Proskurov. I am the first author of the paper titled "Fast Lung Localization in Computed Tomography by One-Dimensional Detection Network." Today, I will talk about a neural network solution that helps us get useful information about a computed tomography scan. First, I will briefly talk about how a CT scanner works, about the data which we have to work with, and the problems we face. Then I will describe a general approach that solves some of the problems. And in conclusion, we will look at the neural network implementation and test results. Computed tomography uses the same technologies as conventional X-rays to create a three-dimensional image of internal structures. The CT machine rotates the X-ray source in a circle around the patient body. By measuring the attenuation of the beam with the detector, a so-called axial slice is created on the opposite side. This is two-dimensional image in which the intensity of each point reflects the density of the internal structure of the object. Having collected all the slices together, we get a voluminous and detailed description of the structure of the internal organs of a patient. Our research team develops various algorithms designed to process computed tomography images. In the process of their implementation and attempts to introduce them into clinical practice, we faced various problems. For example, if the patient moved during the scan, the radiologist has to perform the procedure from the beginning. Unsuccessful result can still be processed. Another example, during this survey, several different areas of the body may be scanned, such as head and lungs. Also, difficulties can arise when sending data over the network. The sequences of axial slice are rarely lost, and we can simply trace them. In combination with different post-processing, at a radiological station, we are faced with the fact that one study almost always contains the result of several scans. This means that before running the main algorithm, we only need to select one series of Excel slides. If there is no suitable series, then we should not run the main algorithm, but we refuse to work when we must explain the reason. To solve these problems, we need a strict label containing reliable information about the anatomical structures contained in the slice. Usually such a label is in metadata of the slice, but as practice shows, this cannot be trusted. Therefore, without looking at the image itself, it is impossible to know what is in our current work. Our target is the lungs. The lungs are a large organ, which means that we are not interested in millimeter precision in their localization. The knowledge of the approximate location of each axial slice in the conditional coordinates of the human body will be enough for us to localize the lungs. Suppose you and I make a decision that if the axial slice is a shoulder level, we say that it is at zero level. If it is at the level of the pelvis, then we conclude that it is at the level of 1. Then the axial slice at the chest level should receive an estimate of about 0.3. At the level of the abdomen, about 0.8. And at the level of the eyes, minus 0.3. This scale should be the same for different patients. It should be independent of the body type and individual characteristics. In the work, unsupervised body part regression, an approach to solving this particular problem was proposed. The key feature of this solution is that to create such a scale, the algorithm relies solely on knowledge of the sequence of slices and the distance between them. This algorithm does not require human markup. I note that we have implemented a similar solution to this problem even before reading this publication. But still, having for our solution, I find more elegant we refer to the authors and try to stick to the terminology they introduced. SSBR is self-controlled body part regressor, is implemented as a classical convolution neural network. This model receives one axial slice as input and gives it a numerical estimate. The numbers themselves don't matter. Only two facts matter. First, the scores for subsequent slices should increase monotonically. Secondly, estimates containing similar anatomical structures for different patients should be the same. Using linear transformation, the scale can be translated to any interval For example, as in the example from the shoulders to the pelvis. SSBR shows excellent quality. However, we asked ourselves the question: why force the neural network to process each slice separately? The summation image, which is very similar to an X-ray, shows absolutely everything. Indeed, looking at such an image to each line, even a metro can easily conclude at what level the corresponding axial slice is located. Processing a two-dimensional image is an order of magnitude shifter than processing a three-dimensional image. And the quality should not deteriorate much. We decided that projection alone was not enough. It was decided to fit into the fully convolution network 4 types of projection. Obtained by different methods of aggregation the entire volume at literally this model works and most often themselves. Using the transfer learning technique, we transfer knowledge about the subject area from SSBR to FC. A few words about training the SSBR networks. The original works use a combination of two error functions. The first analyzes the model for ordering order lines. The second analyzes the level assessment. The authors argue that SSBR is not trained with simpler functions. We solved this problem by changing the approach to sampling training examples and the principle of gradient accumulation. This made it possible to use the mean square of the difference as a loss function. We also apply various augmentations to the input data. For example, augmentation using rotation made it possible to obtain educate assessments for patients leaning on free side. Also, unlike the original work in which VGG16 is used, we use ResNet, and as a full convolution unit network. A similar architecture with ResNet blocks as filters. In order to be able to compare our models with the original SSBR results, we trained our models on the same depletion dataset. We validate all models on 3 other open sets. We choose rank correlation as the main metrics by which we can judge the quality of the model. It allows us to assess the monotony of the increase in the neural network assessment. As we can see, the SSBR model shows excellent results, and the FC is even better. This is due to context. Small errors are automatically corrected based on adjacent values. But this does not mean that the overall quality of the FC model is superior to that of SSBR. Having set the task of filtering slices that do not contain areas with lungs parenchyma, lung parenchyma, we see that the quality of localization of the lung.
Excuse me, 1 minute, please.
Yes, thank you. That the quality of localization of the lungs themselves using a full convolution network is slightly worse than SSBR in all respects. Naturally, this error accumulates at the boundary slices, taking into account the fact that SSBR process quadratically more features. Such a result in nature. However, the solution proposed by us gives a disproportionate large increase in the speed of solving the problem, and requires much
1 minute,
less
please.
computing resource. Thank you for your attention.
Thank you very much. I'm sorry we have no time more for this interesting presentation. It's very good. It's very good presentation. Do you have, dear colleagues, do you have any questions to presenter? Okay, in this case, I ask one. Your work is very close to problem of ROI detection, region of interest detection, and for two-dimensional images, there are methods of bounding box regression that find interesting regions for the following analysis, prediction, and other. Why you focus only on 1D slices and not try to solve bounding box problem in three-dimensional volume?
Yes. I think that my colleague will be able to answer this question better, Anwar.
Yeah, let me help. The answer is we train our network in a completely self-supervised manner. And for this matter, we don't actually need the supervision. We don't actually need the data with the labels. So we don't need bounding boxes for our task because we use a self-supervised network and train it in a self-supervised manner. So with this approach, you are able to use a massive amount of data, much larger data set. For example, in our practice, we have used thousands of unlabeled, uncategorized 3D CT images. And it's much cheaper. You don't need to waste time, money, resources on making labels, on making bounding boxes. And for the second part of the question regarding why do we use a one-dimensional regression, one-dimensional detection, so partially this is because we trained in a self-supervised manner. We simply don't have labels, we simply don't have bounded boxes. But the second part of the answer is the main purpose of this network is to fastly localize the region of interest. And then we use a much sharper network to accurately delineate and accurately segment the region of interest. But the purpose of this particular network is to do it very fast. And we could allow for some errors on the boundaries. That's not a big deal, but we need to do it fast. And this allows us to greatly decrease the size of the volume to analyze by a larger network. So a larger network works slower, but it's much more precise. So if we could, let's say, decrease the initial volume of the CT scan from, let's say, a few hundred slices to, let's say, 100 slices, localizing the region of lungs, then this much larger network will process them much faster. Yeah.
So thank you very much. Thank you very much for answer. It's perfect. And we go to the following presentation: predicting the grade of clear cell renal cell carcinoma from CT images using random subspace KNN and random forest classifiers. Ahmed Kuragov. I'm sorry, Ahmed Kuragos. Sorry for. Are you ready?
Yes, I'm ready.
Could you start, please?
Of course. Hello and good morning, everyone. Can you hear me?
Yes.
Okay, thank you.
Yes, please.
Hello and good morning, everyone. My name is Ahmet Karagöz and my teammate is Albert Güveniş. I'm a graduate student at Boğaziçi University studying biomedical engineering in Turkey. Thank you so much for having me here today, and thank you so much to the organization committee for this very beautiful event. My topic is predicting the grade of clear cell renal cell carcinoma from CT images using random subspace KNN and random forest classifiers. Here is my outline. I will talk about these topics one by one. And first, I want to give you some about our study. First of all, what is RCC? RCC is the renal cell carcinoma, which is the most common kidney malignancy. And one of the subtypes of RCC is clear cell renal cell carcinoma, which is the most common subtype of the RCC with the 75% occurrence rate. And only in the US, about 61,000 new cases and approximately 14,000 deaths were reported only in the 2015. And what's the grade and what's tumor grading? The tumor grade indicates aggressiveness, which relates to how quickly the tumor is expected to spread. And the tumor grade is an important parameter for selecting the optimal therapy, treatment plan, and prognosis, hence their outcomes. According to who is up RCC grading system, there are 4 grades from 1 to 4. And also it's very common approach to classify these grades as high and low grade. High grade represent here the grade 3rd and 4th grade, and low represents the 1st and 2nd grade. In today's world, current gold standards for tumor grading is pathology reports of the biopsies, and we want to change this with the medical imaging studies. And what's radiomics? Radiomics is a quantitative approach to medical imaging, which aims at enhancing the existing data available to clinicians by means of advanced mathematical analysis. Through mathematical extraction of spatial distribution of signal intensities and pixel interrelations, radiomics quantifies texture information. And what are these radiomics features? There are 3 main types of radiomics features. One of them is first order statistics, second is shape-based, and third one is texture features. All of these listed features are can be categorized as 3 main categories. In this study, we aim to create a novel machine learning model using radiomic features obtained from 3-dimensional computed tomography images in order to accurately predict the correct who-is-up grade of clear cell renal cell carcinoma patients preoperatively and non-invasively. There are 2 main challenges of this study. One of them is small data set. We have a relatively small data set with 143 patients, and our data set are unbalanced because while we have 97 patients with low grade, we have only 46 patients with the high grade. If I need to give you some detailed information about the data set, we get this data set from the Cancer Imaging Archive. It's publicly available. Originally, there are 210 patients in our data set, but only 143 of them are clear cell renal cell carcinoma. In addition to CT images, we have also 3D segmentations of kidney and the tumors in our dataset. And also, there are some additional information, more than 30 different types of information included, age, body mass, and smoking. Here you can see a summary of a radiometric study. Firstly, we need to get the images, image scans, and we need segmentation of the images and region of interest or volume of interest. Before the feature extraction, we need to standardize all of the images, because these images can be obtained from the different institutions or different brand of machines. With the feature extraction, we get very mass amount of feature, and we need to select the best features and most informative features from these feature sets. And classification and model training should be done with selected features. What we are doing in the pre-processing step, when we look at the dataset, we found out that all of the pixel sizes and slice thicknesses are different. So we need to standardize these images. We resampled all the scans to the 1 millimeter cube voxel resolution to obtain robust and stable features. And we also normalize and discretize our gray level values. We did all the feature extraction processes in the 3D slicer software with the PyRadiomics extension. We extracted features from the original images and also filtered images. We use two different types of filters. One of them is Laplace transform, another one is wavelet transform. In total, we obtained 1133 features from each CT scan. Before the feature selection process, we need to pre-process our selected features. First, we split our data into two, as train and test data. And as I said before, we have an unbalanced data problem. To overcome this problem, we use smooth algorithm. We upsampled our minority class and balanced our data. And we also normalize our features, because range of distribution of each features are very different from each other. And we normalize these features with disease for normalization and obtain a stable feature distribution. In the feature selection processes, first we apply a correlation coefficient analysis to find the highly correlated features. We need to eliminate the highly correlated features because they are not conveying us additional information about the data. So we eliminate the features with a correlation higher than the 0.9. Then we obtain 253 features.
2 minutes, please. 2 minutes.
Okay, thank you. And we calculated feature importance with the random forest algorithm, and we also applied sequential feature selection to find the 15 best features. In the model training, we trained random forest and the random subspace KNN, because we know that the performance of this model from the previous studies. We use 5-fold cross-validation to avoid overfitting, and we also tried more than 5,000 combinations to find the best hybrid parameter of the models. And performance of these models are evaluated on the whole test dataset. As a result, we obtained 86% accuracy with the random forest and 90% accuracy with subspace KNN. And if we look at the ROC curves, we get 0.8 area under the curve with the random forest and 0.88 area under the curve with the random subspace KNN. As we can understand from the results, random subspace KNN algorithm resulted in higher accuracy in this dataset with our setup. And we can also understand that 90% accuracy could be obtained using a small and imbalanced dataset with using ensemble learning and smooth methods. As a future work, it should be conducted with larger data from centers and implementation in clinical institution, clinical settings. In conclusion, our independent test results show us that acute tumor who is upgrading may be performed preoperatively and non-invasively by using a reduced set of radiomics features and ensemble learning-based machine learning algorithms by using typically encountered small data sets. And thanks so much for your attention.
Thank you. It's great. It's great presentation. We have two questions for you. One from Uliana Lyakova. Could you ask your questions, please? Uliana, we are here. Are you here?
I can see questions from the chat box.
Yes, from chat. Okay. If you're ready to answer, please answer on two questions from chat. The first question, could you please specify what types of wavelets and how many levels of wavelets transform were used for feature extractions? And second question, have you tried to use a completely end-to-end pipeline, thus avoiding RF, KNN, e.g. taking encounter part of your segmentation network and train it on classification?
Thank you for the questions. For the first question, we tried 8 different wavelet transform features with the high and low transforms. In radiomics features, they give us opportunity to transform the features before the feature extraction, transform images before the feature extraction. And I used the 3D slicer to extract these features, and I use 8 different wavelet values to transform images. And for the second question, we didn't use end-to-end pipeline yet, but we are now trying to find different methods other than the RF and KNN. I think that's all.
Thank you, Ahmed, for the answer.
Thank you very much. Do you have any questions, any other questions to? Okay, thank you very much. And we go to the next presentation. Augmentation in neural networks training for person identification by iris images. Yulia Ganeva. Are you here, Yulia? Are you ready?
Yeah.
Let's start, please.
Can you hear me and see the presentation?
We see the program. Oh, okay, it's good. Perfect.
Okay, good. Good day. My name is Yulia Ganeva. I am a student of the Samara National Research University, and today I want to present my report of the topic of augmentation and neural network training for person identification by iris images. Iris identification is one of the most accurate and reliable biometric identification methods, as the iris texture is remarkably stable over time. On the right side you can see an image of the eye with the pupil, iris, and sclera marked. Within the framework of the research, the goal was to develop a method for person identification by iris images using convolutional neural networks. In accordance with the set goal, the following tasks were formulated. Analyze existing solution, select a data set to evaluate the performance of the method, implement a method of personal identification by iris images, conduct experimental research, and draw conclusion. This slide shows a standard pipeline of iris recognition. It consists of the following steps: segmentation, normalization, feature extraction, and classification. In many works, the augment method half transform and others are used to segment the iris of the eye. The normalization stage in many works is implemented as a transformation of a localized region of the iris from a Cartesian coordinate system to a polar coordinate system. To extract feature from a normalized iris image, many works use a Gabor filter, a log Gabor filter, a discrete cosine transform, and other. Also, in some work, after feature extraction, a stage of data dimensionality reduction is added. For classification, many works use the following machine learning algorithm: a random forest classifier, the support vector machine, and other. This slide provides a summary of the selected dataset. The MMU iris database was used as dataset of iris images. The database contains 5 images for the left and right eyes of 35 people, which gives a total of 450 images. The problem of multi-class classification is being solved, where the number of classes is 35. To evaluate the quality of the segmentation stage, all database images were manually segmented. This slide provides an overview of the proposed approach for iris identification. The proposed approach for person identification involves a training stage which consists in general of the following steps: segmentation of all iris images in a training dataset, normalization and application of augmentation to the segmented images, training selected neural network using augmented images. The utilization of the training network, i.e. the identification by an iris image, assumes the segmentation of the image. Previously, we proposed a method for the segmentation of iris images using a convolutional neural network of the UNet architecture. On the slide below, you can see the title of the article, which details the segmentation process and experimental research. To improve the segmentation quality, we selected the most suitable hyperparameters for training a neural network, namely learning rate, batch size, and use augmentation, which allow us to expand the training data set. The most suitable hyperparameter for training a neural network turned out to be a learning rate of 10-4 and a batch size of 30. When expanding the training dataset, geometric transformation were used, brightness transformation, and other. You can see an example of segmentation on the right side of the slide. Left is original image, middle is ground truth segmentation mask, right is segmentation result using convolutional neural network. After the segmentation stage, it is necessary to form a training data set fed to the input of the neural network. We can use 2 methods of forming a training data set. The first method is normalization and augmentation based on horizontal cropping. With this method of forming a training dataset, normalization consists in transforming the iris localized texture from the Cartesian coordinate system to the polar coordinate system. Next, augmentation was implemented, which was applied during the convolutional neural network training to the image obtained after the normalization described above. With this method of forming features, augmentation consists of random cropping of the images entering the input in the horizontal direction. The second method is normalization and augmentation based on random mask selection. With this method of forming a training dataset, normalization consists of cropping and scaling image to a fixed size. Next, the augmentation is implemented, which consists of superimposing a mask on an image selected at random from a set of true segmentation masks. It should also be noted that in both classes of augmentation, geometric transforms were applied, namely random image rotation, random cropping in the vertical direction, and brightness transformation. According to the proposed approach, a convolutional neural network performs feature extraction and classification. The data obtained by one of the 2 methods of normalization and fed it into the input of a convolutional neural network using the appropriate type of augmentation. Training and accuracy comparison have been performed among the following convolutional neural network architecture: DenseNet, InceptionV3, and EfficientNet. This slide shows the diagrams of the selected convolutional neural network architecture. Now I will briefly talk about each of them. DenseNet is a neural network architecture for solving image classification problems. This architecture peculiarity is that all operations divide into blocks, and each block is connected to all others. It should be noted that the feature are concatenated, not summed up. This feature helps combat gradient fading and allow feature to propagate. EfficientNet is a class of new model obtained by analyzing scaling and balancing among such hyperparameters as network depth, width, and image resolution on the network. The author presented an approach based on uniform scaling of depth, width, and the resolution with fixed proportion between them. Inception v3 is a widely used convolutional neural network architecture from the Inception family. A feature of this version is the ability to reduce the convolutional operations computational complexity by combining several convolutional filters of different size into a new filter. As a result of combining a symmetric filter, we get fewer parameters to train compared to by symmetric filter. This slide shows the result of experimental research in the framework of experimental research with different hyperparameters such as the learning rate and the batch size. The models of convolutional neural network presented on the previous slide were trained. The training data set include 2 right eye images and 2 left eye images for each person. The result is 180 images. The validation sample was complete from the remaining images. The result is 270 images. Next, the previously described preprocessing was performed on the training data. In order to control the quality during training on neural networks, the categorical cross-entropy loss function was used. The formula for calculating which is present on the right in the slide. Adam was chosen as the optimizer determining the mechanism for updating the weights. A series of experiments were carried. Each neural network with the corresponding type of normalization, augmentation, and specified hyperparameters was trained by 1,000 epochs. The classification accuracy was assessed using the formula presented on the right side of the slide. Accuracy is the percentage of correctly classified images in the validation set. The cross-entropy and classification accuracy was estimated using the validation sample to monitor the training process at the end of each training epoch. Figure 1 shows a graph of the classification accuracy dependence on the selected hyperparameters for neural network with augmentation based on horizontal cropping. Figure 2 shows a graph of the classification accuracy dependence on the select hyperparameters for neural network with augmentation based on random max selection. Tables show the best result of each neural network model's classification accuracy and selected type of augmentation. It has been experimentally established that all the studied architectures of neural network and augmentation make it possible to achieve a high-quality classification of the iris. In this paper for person identification by iris images, we compared 3 neural network architecture for 2 types of augmentation for neural network training. The neural network approach is a very good tool for the identification of person by iris images. The best result was shown by convolutional neural network of the dense net architecture training with augmentation based on a random selection of segmentation mask. Thanks for your attention. If you have any questions, then I will try to answer them.
Thank you very much. We are writing some questions from our colleagues. Dear guests. Okay, one question from Anwar Kurmukov.
So I could ask it myself. So Yulia, thank you for this great presentation. I have only one question. Have you analyzed the main sources of errors? So I mean, why do some samples, when your network make an error, why it happens? What are the main reasons?
Why I use this neural network?
No, so I believe that this task of person identification, it could be very sensitive for the person on which your network make an error. So for example, if you detect a criminal on a surveillance video, right, you don't really want to accuse somebody who is not a criminal being a criminal by your network. So the question is, have you analyzed the cases, the images, when your network failed? And why did it fail? So maybe some image distortion or unusual angle of view, or I don't know, different weather, like rainy weather or night photos, something like that.
Okay, this approach developed for relatively clear data set, and develop a method for relatively unclear. That said, is a good idea for future work. Unfortunately, we don't research so complex situation.
Okay, fair enough. Yeah, thank you.
Okay, thank you for questions.
Thank you very much. And one question from me. Some technologies that's based on this problem of subject identification, and some researchers use not only usual classification problem, but use something more complex approach like triple loss and cosinus metrics for obtain max margin the division between different classes. It's very important for these tasks because when you train neural networks on new data and add new users or subjects to this data, this system can find some problems with precision of detection the previous people. For example, if you have 100 people, precision is good, but if you add some more, 100 people, some previous people can provide very wrong results, and this is very sensitive topics for problems for systems that makes subject identification. Do you try any approach to solve this problem, or maybe you make some studies in this field?
Okay, thank you for your questions. Yes, I agree with you that many works used triplet loss and other method, but developer system can use, for example, for feature extraction steps. And I research this approach. I use feature use this trained neural network for feature extraction and output without softmax layer. I filed for other classification, for example, SVM with different kernels, and it shows a very good result.
Thank you very much. We have time for one more questions. Maybe some people want to ask. Okay, in this case, we go to the next presentation, modified UNet with different attention mechanisms for acute ischemic stroke segmentation using non-contrast CT. Sergey Pnev. Sergey, are you ready?
Yes, of course. Can you hear me well?
Yes, let's start, please.
Oh, no, it's not. 1 second. I'm sorry. One more. Can you hear screen?
Unfortunately, we see only black screen.
Only black screen. One minute, please.
Okay. We have some times.
And now?
Yeah, good. Let's start, please.
Okay, thank you. Let's start. Hello, colleagues. My name is Sergey Pnev, and I and my colleagues, Andrei Tulupov and Vladimir Berekov, want to present our work. Today, modified UNet with different attention mechanisms for acute ischemic stroke segmentation using non-contrast computed tomography images. So today I will talk about our motivation for doing this work, about the role of computer tomography in the diagnosis of acute stroke, data acquisition, attention, and our architecture, and a little about our segmentation results and future plans. So let's start. The motivation of our work is to development and improvement of computer technologies for automatic recognition of acute stroke using non-contrast computed tomography brain images. So stroke is a sudden impairment of brain function, and there exist two types of stroke: hemorrhagic or bleeding stroke and ischemic stroke due to blockage of a blood vessel supplying the brain. And an ischemic stroke consists of a ischemic nucleus zone where neurons will die in 6 or 8 minutes and nobody can save them. And the penumbra, where in which the blood supply is lower than necessary, but neurons can be saved in 84, 88 hours. Thus, the sooner treatment begins, the better the chances for the patient's recovery. Instant non-contrast computed tomography scan and correct interpretation allows one to reach the correct diagnosis and immediately begin treatment. Contrast tomography, computed tomography is non-invasive, inexpensive, fast, and widely used method for this task. Manual analysis and interpretation of non-contrast CT images is rather hard. It's known that even highly qualified specialists can make erroneous decisions with sufficiently large probability, up to 10%. An anonymized sample of patients was obtained from the database of International Tomography Center of Siberian branch of Russian Academy of Science, and where 25 patients with diagnosed ischemic acute strokes were used in our study. All images were manually segmented by radiology specialists from ITC USBEREIT. Let's talk about UNET and our architecture. UNET is a basic convolutional neural network, consists of two paths. First encoder that selects the necessary features and encode them, and the decoder that unfold or upsample feature map into segmented image. And also there are some skip connections that save gradient and used for better convergence of a network. We use it as a base. For our architecture, in that we propose to use FPA model as the bottleneck to allocate and aggregate context and increase the receptive field of a network. Also, on the skip connection phase, we use a convolutional block attention model to have the model network to highlight the most important features and the allocations. And also we use a double attention gates with spatial attention mechanisms to allocate the location of the most important features. Little about attention. Human attention is a selective focus of perception on a particular object and increased interest in the object in order to obtain any data. And attention in neural networks is a mechanism by which a network can weigh features by level of importance to a task and use this weighting to help achieve the task. The goal. So feature pyramid attention, this model combines features from 3 different scales, as you can see on the screen, with convolutions with different kernel size. And then parallel, there is a branch of global pooling to improve the performance of the model. The motivation to use FPA, because we wanted to look at the resulting feature map at different scales, so we don't miss anything important. Convolutional block attention model, you can see it on the slide. You can see its structure. It consists of sequentially applying channel attention and spatial attention. In the channel attention model, we aggregate the most important information from feature map using maximum pooling and average pooling operations. Then we feed resulting vectors in MLP and concatenate resulting vectors after MLP and normalize with softmax. So we get channel attention map. In spatial attention, we use maximum pooling and average pooling too, but we use it along the axis. And after that, we use convolution layer with kernel size 1 by 1 and normalize with softmax. Also, in the end of CBAM, we concatenate the input feature and the refined feature. Also, we provide some experiments with focal Tversky loss function, because dice loss and the combination of dice loss and binary cross entropy, the main limitation of this loss is that false positive is equal to false negative, which in practice leads to high precision but low recall. So some implementation details: we use Adam optimizer. We train each model during 200 epochs, batch size 6. Also we use scheduler reducer, and split our dataset in such proportion. Also we used image augmentation like horizontal flips and small angle rotation. Here some qualitative results, some results of segmentation. You can see that despite the small amount of data, our architecture segments the images quite well. On the left is image and the right is prediction. Ground truth mask is blue and the found segmentation prediction is red. We did experiments using different UNet configurations, and we can see in the table that UNet using all modifications win in dice index, but lose in UNet with modifications without double attention gates. And with results from networks that trained with a combination of dice loss and binary cross entropy loss. On this slide, we trained similar architectures, but trained them with the focal Tversky loss function. Dice and recall are lower for all indexes, but precision has increased for almost all models. This may indicate that the model tries during training to make all found items relevant or find all relevant, but doesn't take the ones it is sure of. So experiments have shown that the usage of attention mechanisms in different configurations allows to improve the quality of a network for medical image segmentation tasks. And in our case, training network with focal Tversky loss increases precision, but reduces the dice index and recall. And we plan to extend the sample of acute stroke CT images and create separate branch as a model for boundary segmentation with focal Tversky loss. So thank you for your attention, and I would like to thank the conference organizers, reviewers, and my colleagues, Andrei Tulupov and Vladimir Berikov. I can try to answer your questions.
Thank you very much. We are writing some questions. Maybe Anvar Kumkov want to ask one more questions.
Yeah, so my question is, have you classified two-dimensional slices or three-dimensional volumes?
At the moment, we used two-dimensional slices, but now we're collecting data with three-dimensional because it's more objective at the moment.
Yeah, because like in many studies, researchers uses two-dimensional slices, but like computer tomography and magnetic resonance images, they're inherently three-dimensional images. So it's like if you split the picture of the cat into parts and predict. So it would be much more precise to use three-dimensional volumes and report metrics on three-dimensional volumes. But for the segmentation part, 2D probably works too. Yeah. Okay. Thank you.
Thank you. But where exists, as I know, one data set with three-dimensional slices about strokes, and it's from ISIL's competition, and it's not really good data set, and we try to collect our data from tomography center, 3D data, as you said. Thank you.
Thank you.
Thank you very much. One more question from me. Okay. There are many works that use modified UNet and exploit this idea to different kind of medical images. Could you formulate and say what's the major advantages of your approach and why other researcher should use your ideas in his work and his technical solutions for biomedical tasks?
Yeah, okay. At the moment, we tried to provide some experiments with different types of attention, such as the CBAM, double attention gate, the FPA, and at the moment, transformers are the tip of attention. And as I said, maybe researchers can take from our work results from different types of attention models, something like this.
Thank you very much.
Thank you.
I'm waiting for more questions. Okay, there are no questions. In this case, we go to the next presentation. It's work of Uliana Lyachova, methods of cleaning hair structures for intellectual image classification of skin neoplasms. Let's start.
Oh, good day. Is all right with our signal?
Yeah.
So Pavel Lyachov and Uliana Lyachova are here. We are both co-authors of the presented work. And do you see our presentation?
Yes.
Okay. Good day again. We propose your attention a work entitled "Method of Cleaning Hair Structures for Intellectual Image Classification of Skin Neoplasms." The work will carry out at the Department of Mathematical Modeling, North Caucasus Federal University, Stavropol, Russia. So I propose Uliana to present our work, and after then we will answer your questions.
The slide shows a short outline of our report. Skin cancer is one of the most common types of malignant lesions in the body. The slide shows a statistical map of the number of diagnosed skin cancer lesions in the population without regard to age and gender. The main percentage of the population of the northern hemisphere of the ear belongs to first and second skin phototypes according to Fitzpatrick classification. The phototypes are genetically unadapted to the high level of ultraviolet radiation and are proposed to melanoma. The use of artificial intelligence can significantly improve the accuracy of skin cancer diagnostics carried out by specialists. However, the main problems of using artificial intelligence in the field of dermatology is the low accuracy of recognition and classification systems. Our research proposes a method of identifying and cleaning hair, as well as evaluation and effectiveness of method using a pre-trained neural network. This method allows a preparation and dermatoscopic images for automatic classification. The preference of variance noise structures, such as hair, can change the size, shape, the lesions, and pattern of the texture. This significantly complicates the use of systems for automated recognition and classification of pigment skin lesions. The slide shows a detailing diagram of the proposed hair cleaning method from dermatoscopic images. RGB dermatoscopic images are fed to the input of the method and the color components are extracted. Image processing is performed separately for each color components. The slide shows an example of how the hair cleaning method works. To identify the location of hair structures on the image, a morphological operation of clothing. Then the original images is subtracted from the one obtained as a result of the clothing operation. The next step is threshold zeroing of pixels. After that, the morphological operation of dilatation is performed to expand the boundaries of the hair structures. As a result, we get a cleaning image. Nowadays, convolutional neural networks are the most optimal for pattern recognition in the field of artificial intelligence. This type of the neural network includes input and output layers, several hidden layers represented by convolutional layers, pooling layers, and fully connected classifier. The field shows the system of neural network classification of pigmented skin neoplasms from photographs with the stage of identifying and removal hair structure. The database of cleaning dermatoscopic images from the open archive of ISIC melanoma project was selected for modeling. The selected images were categorized into the 10 most significant diagnostic categories, which are present on the slide. The slide shows examples of dermatoscopic images that have passed the pre-process stage. To assess the quality of the proposed method for identifying and cleaning hair structure on dermatoscopic images, a convolutional neural network was trained on pre-processed and unprocessed bases. The application package used for the simulation, as well as the system parameters, and presented on the slide. For training, the neural network architecture AlexNet was used, which was pre-trained on a set natural images ImageNet. With further research, additional training was carried out for other neural network architectures to confirm the results obtained. The slide shows the learning results of the modified VG16 as well as the nets, QuasiNet, which were pre-trained on the ImageNet natural image set. The highest indicator of the accuracy of recognition of pigment skin lesions was achieved using the neural network classification system with a stage of preliminary hair cleaning with the AlexNet architecture and amounted to 80.81%. The increase in recognition accuracy when training neural network classification system with a stage of preliminary hair cleaning ranged from 0.16% to 3.17%, depending to the architecture. The pre-processing method proposed in the work made it possible to prepare images for further automated recognition and classification of pigment skin lesions. The use of the proposed method for identifying and cleaning hair structure as a preliminary stage for processing dermatoscopic images with allow images recognition and classification system to increase the efficiency and steep diagnosis. The proposed system of neural network classification of dermatoscopic images of lesions with a preliminary stage of identification and classification and hair removal will facilitate the work on the recognition and diagnosis of pigmentary neoplasms. Thanks for your attention. We are ready to answer your questions.
Thank you very much. I ask one questions and maybe other ask more one. Some people's work with idea that image should be filtered before following processing, but maybe more suitable position. It's provide augmentation technique for neural network, and you can add hair to your images of melanoma and process through neural network. Could you compare these two approach and why you choose filtering approach for your application?
Thank you for the question. The augmentation is a very important technique in convolutional neural networks technologies nowadays, and we are planning to add this technique for our future research. But the task what we working within this work is removal of hair structures and filtering, both fear filtering or maybe order statistic filters are not demonstrates not so good results on the task of hair removal, and therefore we decide to use morphological operations as a preprocessing stage. The morphological operations allows us to effectively remove hair structures and without loss of quality of skin neoplasm. This allows us demonstrate that neural networks could recognize better skin cancer, and we think that our result will help to dermatologists in their diagnostics.
Thank you very much. And I ask more questions. Do you check that your approach is stable if we change orientation of photography and angle of photos? And also, what happened if focus was imperfect and some blurred images, some blurred hairs obtain on images?
Thank you for the questions. Today we are trying to use our method in mobile application, and we are testing now how these equations can relate to the result, but this is a field for future research in our topic.
Okay, thank you very much. We have some break from this time to sorry.
I'm sorry, do we
yes.
have time for one question?
Yeah, of course.
So could you please move to the slide with the performance metrics, the resulting table? Yeah, right. So am I right that you use multi-class accuracy?
Could you please repeat?
Have you used multi-class accuracy to measure the scores? So these scores, are they multi-class accuracy?
No, only one class accuracy we use.
Okay, but you've shown that you have like 8 or 10 different diseases, different types of skin lesion. No.
Maybe you can present confusion matrix.
In this presentation we can't, but we can send them to email or demand.
Yeah,
okay.
Okay. So thank you. Okay, never mind.
Okay, dear guests of our conference, we have sometimes it's a small break, but I encourage you to start discussion on free topics in any types, because unfortunately we can't join together and discuss our ideas, our mentions about presentation. on coffee break, because we have no coffee break, because coffee only in our homes or in our work. For this reason, I ask you about say some mentions about other presentation, about some interesting ideas, interesting solutions. For example, I'm personally very interested in the first presentation of Anvar Kurkumov, because it's very unusual and original ideas, but also presentation was very good, and we have some time for discuss it, because the following keynote speakers start speech at 12:30. After we have 15 minutes. Anvar, maybe you say some opinion, ideas about other works, about other, yeah.
Yeah, I just want to add something to your last question to the Uliana about translating and moving images. So basically, in recent years, there were several papers which shows that if you use an additional penalty to ensure that your network is actually translation invariant to the so the predictions of the network is translation invariant. That means that if you take the same photo, for example, you rotate it to like 19 degrees, you pass it to the network, and you obtain a prediction. That predictions should coincide with the prediction of this network on the original photo before rotating, right? So you simply rotate the image, you make a prediction, it should be the same as if you pass the original image. And there are several studies that shows that if you use this additional penalty to ensure the consistency, then your overall classification will be better. So maybe it would be useful for the authors for the Uliana to take some of these ideas. And there are also several other translation techniques, right? You could not only rotate the image, but you could also move it, like small morphological deformations also works.
Thank you for the comment. As we said, that different augmentation techniques are planned to perform in our future research, and we will try to use different angles and maybe other techniques for improving our system. Thank you.
Yeah, just a small addition is that it's not an augmentation technique itself. So augmentation is fine, and it almost in all cases it works. But what I'm saying is that you could use additional penalty to ensure consistent predictions on the images that was transformed. So it's not just an augmentation, you need to introduce an additional loss into your overall loss. So for example, you could add a simple difference between if you put original image and rotated image into the same batch, you could add a penalty term into the loss function, which is simply a difference between the predictions on the original image and the rotated image, and it helps a lot in questions like classification some disease on the image. But yeah, just as an idea.
Okay.
Oh, thanks for the idea, and thank you. We will try to study this in the future. Thank you.
Okay, Yulia, are you here? Yulia Ganeva, are you here? Maybe not here. I want to say that in previous conference, we have publication with my colleagues about subject identification problem. We analyze how the physiological human physiology and human physiology effects to problem of subject identification by ECG, by electrocardiographic signals. And from this point of view, our work is close to work of my previous work with my colleagues is very close to work of Julia. And I personally, I am not interested in subject identification, but my colleagues from Ufa city is very interested in this, and I suppose that maybe interested in work with you. Okay, unfortunately, Julia not here. Maybe some other people, maybe Boris or Ahmed want to say something. I encourage you to perform some discussion, because conference, it's not only the presentation, because we understand that our peoples make different topics, and it's very difficult and require a lot of mind power to understand what idea of other people can be bring in our works, and can be bring what we can do together and other. And coffee break is very good time for make it. Unfortunately, we have no coffee break because we can join together in Yekaterinburg, but we can discuss some of our topics here. Vladislav, maybe you're here. Okay. Unfortunately, all people goes to some breaks, and in this case, I switch off my camera and microphone, and we start in 30 minutes with talk of keynote speakers, and we very glad that these people comes to our conference. Yep, let's take some break.
Thank you, Konstantin.
Dear guests, we start after 2 minutes. We are waiting the keynote speakers. Keynote speakers here. Okay. I note that when you go to schedule on the USBEREIT site, you can press on name of presentation, and after this you obtain access to context of speaker and to full PDF paper, because all PDFs already in all preprints already available, and you will choose any work and read them. Okay. Organizers, the main organization committee write me that they tried to call to keynote speakers, and sorry. Okay. We're still waiting the keynote speakers, and I hope he join us very soon. Sorry, I have no. I want to use some time for explain possibilities of our site. If we go to schedule to this page, you can press on name of presentation. And here you can write some questions to speaker. Read full paper, because our papers are available as preprints on conference site. For example, it's first presentation. And also we can press on view contact and obtain contacts of presenter. This can help you to find new colleagues, new ideas, new collaborations, write joint grants, obtain foundation and other important things. Dmitry, are you here? Okay, let's look on the following for presentation. It's speech power segmentation method based on tier energy operator and short time energy analysis. This paper is about, I try to find some interesting images for provide good content on YouTube. This paper has some images about these methods. It's look like, oh, it's fragments of speech. Okay, something goes wrong with keynote speakers. Organization committee write me that some troubles happened, and they detailed situation. Okay, keynote speaker can join us for some reasons, and currently organization committee fix conference program. Okay, I encourage you to read the following papers in the next block of our sections, and prepare some interesting questions for presenters, improve your knowledge in these fields. Maybe it feels very close to things you do, but maybe not so close. But it's very important to understand and accept other ideas, and conference. It's a good time for spread your mind and open your mind and gain new ideas from other groups, other researchers. Yes, I'm sorry, I need to contact this phone to organization committee because something goes absolutely wrong, and we announce changing in program as soon as possible. Dear colleagues, we are sorry for issues with keynote speakers. We change schedule, and keynote speaker will say its presentation. Will tell you its presentation in the next coffee break. Currently, we have a break until 13:15 to the next block of our section.
Добрый день. Добрый день.
Hello, are you hear me?
Да, я сейчас слышу. Thank you,
Oh,
thank you.
sorry. I should repeat my speech again. We're sorry about changes in our schedule. The keynote speaker from this time slot goes to 4013, and for this point of view, we obtain a very big block from now to this time. And also a presentation of Boris Gurevich was bringed from third block of presentation to second block of presentation. And currently we ask about Alan Alimuradov. Are you here?
Yes, I am here.
So sorry, super, very good. Please start your presentation.
Okay. One moment. It's okay.
Yes. Let's start this.
Okay. Good afternoon, dear colleagues. My name is Alan Alimuradov. Let me present my reports of the topic speech prose segmentation method based on integer energy operator and short time energy analysis. The speech prose segmentation task is a classifier of informative section. An accurate detection of the boundaries of the beginning and the end of informative speech section is one of the most important tasks in speech signal processing. Today, the problem of speech prose segmentation is solved in different ways, presented by time and frequency method. Time method includes those based on zero crossing rate, ZCR analysis, standard deviation of articulation function, short time energy STE, and one-dimensional Mahalanobis distance. Frequency method those both based on the analysis of male frequency capital coefficients and linear frequency capital coefficients. The report presents a method for speech prose segmentation based on energy analysis of speech signal fragments using Tiger energy operator and STE, short time energy. The speech prose segmentation method based on energy analysis of speech signal fragments using STE is not widely used in speech replication. The elimination are related to selection and justification of the correct threshold STE values corresponding to voiced, unvoiced speech and process. The speech prose segmentation method based on the STE analysis is built on assumption that the STE values of voiced and unvoiced speech is greater than the energy of voices with background noises. However, this assumption is not entirely correct since the main questions remain unresolved, namely, how much the correct ST values should be greater than the threshold value for correctly segmentation of informative section. Tau is a second-order differential energy operator, which makes it possible to estimate the energy characteristics of a signal. Tau is simple, efficient, and highly susceptible to change in signal amplitude and frequency. At present, Tau has received wide practical application in speech signal processing tasks. The slides show a structural diagram for the method of speech prose segmentation based on energy analysis of speech signal fragments using Tau and STE. The nature of segmentation is a linear deviation of speech signal into fragments. Block 1, calculation of energy characteristics of the speech signal using TEO. Block 2, calculation of STE values for fragments of energy characteristics. Block 3, and determining the speech pause state of fragments. Block 5, based on the calculated threshold STE. Block 4. A characteristics feature of the method is analysis of STE value for fragment on speech signal energy characteristics calculated using TEO. TEO is known to provide good sensitivity to change a signal amplitude and frequency. Therefore, it is assumed that the energy characteristics contain complete and reliable information about the STE. The figure presents an example illustrating the result of calculating the energy characteristics for voiced and pause section using TEO. A and B are oscillograms of 30 million section. C and D show the corresponding section of energy characteristics function. As can be seen from the figure, the function of energy characteristics actually provided full information content of STE values, and analysis of which will improve the efficiency of speech signal segmentation. For correct speech pause segmentation, is the proposed method present a solution to the problem of choosing STE threshold value. In accordance with the physiology of speech reproduction, before pronouncing, a person keeps a frozen initial pause at least 200 millions duration, which correspond to background noise. In proposed to use this initial pause as a source data for the formation of STE values. Determination of speech pause state for the fragments is carried out to verify the following condition. When instigated, the proposed method to effect on the threshold coefficients to the efficiency of speech pause segmentation was elevated in comparison with the method based of energy analysis using STE. The table presents the average values of the first and second kind errors for speech pause segmentation method based of energy analysis using STE and the proposed method. The green background indicates the best achieved speech pause segmentation result. The blue background indicates the value of the first and second kind errors to be detailed. In accordance with the data present in table, and this shows the dependence curve, the first and second kind errors and the threshold coefficient for the speech pause segmentation based of energy analysis using STE and proposed method. The analysis of the obtained result that has revealed that the most optimal values of the first and second kind errors and achieved by the proposed method, 2.6% and 1.95% respectively, with the threshold coefficient value equal to 10. For the original speech pause segmentation, the optimal values of first and second kind errors are achieved with the threshold coefficient value 1 to 2, and they are in interval of 6.31, 8.22, 24% respectively. The slides show an example illustration for segmentation result of 10 seconds speech signal. And conclusion. Summing of the analysis result to following conclusion can be drawn. When comparing the optimal value on the first and second kind errors, the proposed method provides increased efficiency of speech pro segmentation by 5.26% and 5.51 respectively. This is due to good TEO susceptibility to change in signal amplitude and frequency, including abrupt change. The detailing analysis of speech pro segmentation result has revealed that in first kind segmentation errors are mainly observed in the boundary areas between section of speech and process. In accordance with the obtained result, the proposed method for speech pro segmentation based on energy analysis of speech signal fragments using TER and STE can be successfully used in signal processing and real-time speech application. Thank you very much.
Thank you very much too. Great presentation. We are waiting some questions from YouTube or from this chat or from colleagues that join our conference. Okay, one question from me. Do you compare your results with some baseline approach that's usually implemented in some programs like calculation time threshold approach and other?
Sorry, my English so bad. Can we?
I'm sorry. Did you compare your approach with some baseline approach, for example, with usual thresholding?
May I in Russian, please? Данную задачу мы еще не сравнивали, но это будет последующий этап реализации алгоритма сравнения с существующими, чтобы получить широкое применение способами. Это следующий этап реализации алгоритма.
Okay, you answer that this will be performed in the following studies. Okay, thank you very much. Good presentation. I'm waiting for next speaker. It's Andreas Pirkin, features of speech commands recognition using an artificial neural networks. Are you here?
Okay. Меня слышно хорошо, да?
Yes. Could you share your screen, please? And
Good afternoon, colleagues. I'm Andreas Pirkin, postgraduate student. The time of my work features of speech command recognition using a typical neural network. In connection with the current situation in the world and in our country, there are more and more reports in the news about collapsed buildings using the rubble of which people are dead in such of cyborgs as such, and recruit time of people with dogs is sent who are able to detect a person near the surface. With raises the problem of how to look for people who are in the depend of the rubble. Therefore, is was detected to develop a control system for robotics mechanism based on bionic control methods. To increase the efficiency of using the control system for robotics mechanics is proposed to use not one canal for generation a control command, but several canals united by a majority element. These canals represent the registration and subsequent processing of the corresponding physiology signal, such as electromyography, electroencephalography, speech signals. Today, the voice control system is a hot topic. This slide shows a classic function diagram of a voice control system VCS, consisting of a microphone, a processing unit, and a recognition unit. It is important to note that taking into account with software and hardware, the internal structure of the VCS units is more complicated. Speech in the form of sound waves is captured by a microphone, which conveyed them into an energy speech signal. Then this signal is converted into digital form, filtered, segmented into fragment in which information parameters are extracted for further analysis. In the recognition unit, the speech command received by the system is complete with the template from the database obtained during the training of the system. The template database is formatted at the stage of system development is and can be supplement and objective for the use. The system of apparatus for recognition speech command is by implement on artificial neural network. The choice of a suitable neural network structure directly depends on the speed of command execution and on the resources consumed. Analysis of network topologies show that recurrent neural network, more specifically a recurrent bidirectional long short-time memory network or BLSTM will work better. The structure of the neural network is shown on the slide. To train the database, we use Google Speech Common data set. An experiment study on the recognition of a speech command was carried out using the MATLAB software package, with the help of the audio web add-on. A noisy signal was recorded with the command "World выключить off." The signal mask is shown on the slide. After that, the neural network was trained. The network took 18 minutes to train. The analysis of the obtained learning result shows that the keyword recognition accuracy is 91%. Also, on this slide in the right is the result of keyword recognition shown in red graph. As a recurrent six-layer network, BLSTM was used in the study of speech command recognition. The keyword recognition error does not exceed 10%. It is possible to increase the recognition accuracy by replenishing the training base of audio recordings in order to take into account the unique properties of the user's speech. My report is over. Thank you for attention.
Thank you very much. I encourage other people to ask some questions, maybe Anvar, maybe other. Okay.
I have a question.
Да, если можно, по-русски.
Подскажите, пожалуйста, в какой среде была реализована нейронная сеть?
Нейронная сеть была реализована в среде MATLAB.
То есть это уже готовый двигатель, который просто уже использовали, или вы доработали его?
Она была уже готовая, то есть вот эта BLSTM, вот ее начинка уже была готовая, только использовалась уже для конкретных целей, то есть обработки речевых сигналов.
Спасибо большое. Спасибо.
Okay, and one question from me. Do you try to use NEMA2 as library for speech recognition? Because this library based on PyTorch and already include some neural networks for speech command recognitions. Hello, are you hearing me?
Извините, I don't understand.
Do you try to use the NEMA2 library? This is a library for PyTorch framework, which already include a lot of modern architectures for speech recognition. Okay, thank you very much. In this case, I add to chat link in our local seminar when we discuss about this library and its possibilities. I ask about the following presenter, Alexander Dmitriev, analysis of P30 features for target stimulation detection using artificial neural network with small data sets for BCI tasks. Are you ready?
Yes, but the speaker is Nikola Khadev.
Okay, Nikola is here. I would perform the presentation, okay?
Okay, well, let's start.
Just 1 minute, please. Can you see the presentation?
Yes, let's start.
Okay, good afternoon. My name is Nikola. I'm a master's student at Bauman Moscow State Technical University, and the topic of my presentation is analysis of P300 features for target stimulus detection using artificial neural network with small dataset for BCI tasks. According to the World Health Organization, stroke is the third leading cause of death, with about 15 million strokes reported every year worldwide. Of these, 5 million die and another 5 million are left permanently disabled. Recovering from a stroke is a complex and long-term process. Medical rehabilitation is an important part of recovery and helps the patients to maintain and regain lost abilities. There are several methods for post-stroke rehabilitation, which is divided into high-tech methods, physiotherapy, and basic methods. In the past decade, many studies have focused on motor, cognitive, or speech recovery after stroke, where it was highly suggested to use brain-computer interfaces for post-stroke rehabilitation. Brain-computer interface is a technology that gives humans with motor disease the ability to directly control computers or any external devices using only brain signals such as EEG. One of the common used EEG patterns that used to design EEG-based BCI is P300. The P300 potential is characterized by a positive peak approximately 300 millisecond post-stimulus, which is shown in figure 3. The main properties of P300 are waveform, amplitude, and latency. In figure 2, demonstrated a schematic of principal BCI components. Just turn on the video. One of the most steps in designing BCIs is classification, where is widely used machine learning methods like artificial neural networks. It's well known that artificial neural networks works good with big and high quality data sets. However, when dealing with BCIs based on P300, one of the most problems that we suffer from during EEG classification step is the lack of high quality data, which leads to use a small data set in most cases. Accordingly, our first objective was training and evaluating BCI model performance with small data set. The other objectives are represented in this slide. Talking about equipment, the EEG data have been recorded using Neuron Spectrum 5. The equipment characteristics is shown in the right table. EEG was registered via EEG cap following the 1020 system. For the stimulation, we have used a photon stimulator divided by 9 equal cells in the form of 3 by 3 matrix with a light diode in each cell. Each participant was asked to concentrate on one cell during each experiment phase. This cell was divided as a target cell, therefore the other 8 cells were called non-target cells. The experiment paradigms used in our study are clearly represented in these tables. As you can see, in each experiment have been chosen different stimulation parameters like stimulation frequency, size of photic stimulation matrix size with visual and auditory stimuli. An artificial neural network was used as a classifier for P300, which has 2 inputs according to the number of chosen features, 2 hidden layers with 5 neurons, and 1 output, with an activation function ReLU. The ReLU layer defined by the following function. Before the classification process, data normalization from 0 to 1 was obtained using the following equation. Due to the importance of P300 waveform as a main P300 property, cross-correlation value between EEG signal and wavelet marlet has been considered as an additional feature for P300, as this value could give us information about the shape of P300 signal. Cross-correlation has been estimated between P300 and wavelet marlet because of their similarity in signal waveform. For wavelet marlet generation in MATLAB 2016b was used the following function. For comparisons, the data were split according to the stimulation frequency. In the diagram in figure 8 clearly shows the algorithm used for choosing wavelet marlet parameters. In this table shown how the parameters have been varied. Let's get into some examples. In this example, shown the variation process for the experiment 1 with a stimulation frequency equal to 3 Hz. On the right graph, the y-axis indicates the maximum value of the cross-correlation function between the averaged P300 non-P300 response and the wavelet marlet for each set of wavelet marlet parameters, which indicated by axis X. As you can see, this graph appears to be divided into 10 parts. This is caused by the changes of the parameter n, which indicates the number of wavelet points. To determine the most appropriate wavelet-Marlet parameters, the difference between the maximum value of the cross-correlation function with the averaged P300 response and the maximum value of the cross-correlation function with the averaged no P300 response was considered. As you can see in figure 9, where this value indicated by axis Y. Several methods for validation were used for evaluating our model, like area under ROC curve, precision, recall, and accuracy value. In this picture below shown an example of P300 classification. In this slide, the results of our study is represented. In the right table, shown the most convenient wavelet parameters, while in the left table, shown classification results using artificial neural networks, where was used different set of parameters, either amplitude and latency, or latency and correlation coefficient, or amplitude and correlation coefficient. As you can see, best results indicated by green color and worst results indicated by red color. Based on our results, it was observed that the highest classification results were obtained in the first and second experiments, as we got reasonable classification results using testing sets, especially at 3 Hz stimulation frequency. However, the value of recall was considered as one of the most valuable validation parameters, due to the importance of the positive class, which indicates target stimulus. The relatively high results in some experiments are probably associated with dataset size and data splitting method. Therefore, in the future, it's necessary to expand the dataset size and use other data splitting methods. Before I finish, I would like to leave you with the following conclusions. The P300 signal has a high sensitivity to correlation changes, as different recommended values for wavelet-Marlet parameters were obtained, even with similar stimulation parameters, indicating that the wavelet parameters should be chosen individually for each participant. No direct link was found between wavelet parameters and stimulation frequency, while on the other hand, a considerable improvement in classification accuracy was achieved using the correlation function as a P300 feature. So that brings me to the end of my presentation. Thanks for listening. If you have any questions, I would be happy to answer them right now. Just a minute to...
Thank you very much. We have a lot of time for discussion because we go faster than usual.
Okay.
I invited questions from our colleagues, and I ask you 2 questions. First, I see that your area under curve is very high. It's very strange for some approach. Do you check that you have no leakage of test data, train data to test data?
Actually, it's only high in some experiments, like in the first, as you see in the first and the second, while in other experiments, it's a little bit low. And I think it's due to the problems that we have unbalanced classification problem. So we have a ratio is about 9:1 for each class. So the second class is 9 times more data than the first class. So I think the problem is associated with unbalanced classification.
Could you present confusion matrix in this case?
Confusion matrix. Actually, I didn't show the confusion matrix because precision and recall could give us information rather than confusion matrix. But I could send it to you in email or something.
Thank you. And I ask questions about why you choose neural networks, because you use only multi-layer perceptron. This classification is not optimal for any problems. In any works, there are a lot of works which compare neural networks, support vector machines, and extremely randomized forest for classification. And randomized forest, in any case, is better choose for classification problem than usual multi-layer perceptron. And you can use, for example, XGD booster or something for classification of usual vectors. From my point of view, it improves your work. Of course, I understand that you lose neural networks in your work, but really you can obtain much better precision with other methods.
I totally agree with this point. It's a really good point. Thanks for asking. Actually, we use artificial neural. We have a very simple classification problem. We have only 2 inputs, 1 output with 2 classes, and we have a very small amount of data. So we choose artificial neural networks like an initial variant, while in further studies, we would like to expand our data and use other methods like support vector machine and random forest as user suggested. So for sure, we would use it in further studies.
Okay, thank you very much.
Thanks a lot.
The next speaker is Boris Gurevich. The speaker has two sequential presentation. First, it's acousto-optic device application for bioelectric signals wavelet processing and methods for reliable electrocardiographic control of ischemia appearance in investigation with experimental animals. The second, personally, very interesting for me because experimental animals, that's very, very important. Boris, are you here? Are you ready to start?
I'm ready. Do you hear me?
Yes, of course.
Can you look my presentation?
No, could you try to share again?
Yes, just a moment. Just a moment. Just a moment. Yes, just do you see my presentation?
Yes, thank you. We ready to start.
Dear colleagues, I will present you our talk.
I'm sorry. Could you try to press F5 for presentation?
F5, yes, F5.
Slideshow. Press slideshow and
slideshow. F5, yes. Yes, I pressed F5.
Okay, it's very strange because we see the PowerPoint program, but not your. We see first slides, but in PowerPoint. If something goes wrong, we can show from PowerPoint, but better if.
Yes, I see slideshow. Slideshow.
And left.
Yes. Use.
Oh,
yes.
Very good. Thank you very much.
Yes,
okay,
I see.
We are waiting you. And also, I encourage other people to ask questions.
Dear colleagues, I will present you our talk, acousto-optic devices application for bioelectric signal wavelet processing. We are the authors Kirill Zachenko and Boris Gurevich from Institute for Analytical Instrumentation, Russian Academy of Sciences from St. Petersburg. Our talk will connect short introduction. Then the next division is application of optics and acousto-optics for signal wavelet processing and problem statement. Then we will describe acousto-optic processor based on time integration principle. And we will stop at wavelet processing performance using acoustic processors with time and time integration, and with time and space integration. And then I will state short conclusions. The selection of new diagnostically significant markers and signs of different pathologies is one of the most important tasks for both physicians and technical specialists. Develop diagnostic systems which extract information from bioelectric signals, such signals as electrocardiographic, electroencephalographic, and electromyographic. The new authors' method of ultra-high resolution instrumental electrophysiology based on recently development methods of ultra-high resolution electrocardiography is the basis of this investigation. The ultra-high resolution instrumental electrophysiology includes ultra-high resolution electrocardiography, electroencephalography, and electromyography. It is known that a wavelet transformer is a very efficient method of bioelectric signal processing. It allows to extract information regarding the bioelectric signal frequency characteristics, time variations, which is very important, and it becomes possible to know in which time moments certain frequency components appear and disappear. Optical information processing devices and systems can be described by very high operation rate caused by parallelism inherent to the optical processing procedures. They studied signals wavelet transform calculation by means of optical processor is very useful for investigation of signal non-stationarity, definition of the signal specific peculiarities and characteristic elements, and determination of these elements time localization. Optical processing procedures in such processors usually foresee either holographic recording, preferably by methods of dynamic holography, or image recording using different kinds of spatial light modulators. We will consider new way of wavelet processing, application of acoustic devices for this. The basic problem which prevents to apply these devices is that standard frequency range of recording bioelectric signals is below 100 Hertz, and in high resolution mode, this frequency range is below 2 kilohertz. But common frequency range of acoustic devices operation is between 40 and 300 megahertz. So it's too high for perform to perform the devices with operation with bioelectric signals. The possible solution is application of acousto-optic processor with time integration, because the frequency range of the processed signal in by these devices. These devices is limited from the bottom side by accumulation time of multi-element photodetector. And you know that such multi-element photodetectors as CCD arrays or CMOS arrays can be about parts of a second and even several seconds. And if to use special cooling cooling devices, it can be increased up to decades of seconds. You see the simple circuit of acoustic processors based on time integration principle. We use here two Bragg cells which are directed in opposite directions. Hence, one acoustic wave is proposed to the bottom and to the top, and in another Bragg cell, the acoustic wave is propagated to the bottom. And in the first one, we apply the signal linearly frequency modulated signal, which is also modulated by the bioelectric signal to be studied. And in the Bragg cell 2, we use the signal also linearly frequency modulated, but it is additionally modulated by the wavelet, by the mother wavelet function. And in the photodetector, we will record the convolution function, which represents wavelet transform of this studied signal. We use in this device, we use acoustic Bragg cells based on tellurium dioxide single crystals. You see the crystals which are inserted into the housing, and these Bragg cells are fed by the initial signals. The problem, excuse me, please. The problem of the device, which is, excuse me, which is shown in this picture, is that the distribution of signal in photodetector array has is only 2D distribution. Distribution of intensity of current from depending on time, but the wavelet transform is 3D distribution of signal. Hence, it is this wavelet transform is coded in this device, and it is necessary to decode it. In order to simplify and widen the possibilities of the device, we proposed to use additionally acoustic processor with time and space integration. We use additional 2 Bragg cells, which are directed perpendicularly to these 2 Bragg cells and directed up to just up to observer. The photodetector is not a 1D array, but it is a 2D array, such as a matrix. We use the initial signal modulated by LFM signal in the first pair of Bragg cells, and in the second pair of Bragg cells we use the signal modulated, the same signal modulated by wavelet, mother wavelet function, and hence we will obtain the 2D distribution in the array, and from along one coordinate, it is distribution by time coordinate, and in the opposite, in the perpendicular coordinate, it is distribution along duration of the operation, duration of the studied signal cycle. The method of continuous wavelet transform is the most convenient to bioelectric signal processing, because it produces information not only about the signal power frequency distribution, but also regarding time moments where the signal frequency varies. Here you see the continuous wavelet transform, where A and B are parameters defining scale and time shift of function psi, which is known as mother wavelet. Let us consider the acoustic processor with time integration circuit from the point of view of the device use and correlator convolver mode. In correlator convolver mode, the reference LFM signal in such processor can be represented as according to this expression, and photodetector shown in this figure accumulates charge with distribution which is proportional to continuous wavelet transform distribution along A-axis. Hence, the output signal has 1D4. In conclusion, I will say that acoustic devices based on time integration principle can be successfully used not only for spectral signal processing, but they also can provide wavelet processing of bioelectric signals, including those obtained by technologies of ultra-high resolution. Time integration principle provides a performance of correlation and convolution processing of 2 input signals, and if one of them is the signal to be studied, whereas the other one is mother wavelet. So the wavelet processing is carried out in real-time mode. The basic advantage of the discussed processing method is the possibility of their performance in real-time mode as it is allowed by the processing signal time characteristics. The possible deficiency is connected with using of durable charge accumulation time if it attains several seconds or more, because it can cause the photodetector saturation and the response linearity damage. In its turn, it can cause the distortions of the signal processing procedures. Thank you for your kind attention. I'm ready. I'm ready to answer your questions.
Thank you very much. It's very good presentation. I'm very impressed that wavelet transformation, wavelet transform may be presented as real device. It's look very cool. Unfortunately, I know about only mathematical application and how it compute, but acoustic optic device looks very interesting. And here I see Anton Yurievich Dolganov. It's co-chair of the second section. And because she come to us, I write in question. Anton Yurievich.
Yes, greetings everyone. So Boris Simkovich, my question to you is, in wavelet transform, the influence, the impact of mother wavelet function of the results is very huge. So you can use different wavelet functions and you can get different results with different, frequency properties. Have you studied this part? Have you kind of found the most optimal wavelet for your stuff?
You see that in application for electrocardiographic signals, the best way to use wavelets is using of Morley or Gauss wavelets. But if we use wavelet processing of such signals as electroencephalographic, especially evoked potentials, or even complexes such as complex of spike and slow wave, it is very useful to find some new form of mother wavelet, which is close to the studied signal form, and it will it will produce the better results. And now we are working at the problem of formation of such new mother wavelets.
Are they based on existing ones or some sort
No,
of modification, or like purely?
You see that the form of some evoked potentials or complexes require absolutely new mother wavelets.
Okay, thank you.
One more questions from me about this presentation. Could you show some results about ECG processing? You describe system, but I don't understand what's result you obtain with ECG.
Excuse me, the abbreviation you told some abbreviation.
Yes, evaluation.
I think that you see that we have a real base of experimental base, which allows us to perform real experiments of processing. But our very difficult problem is to combine LFM signal with very high carrier frequency. then LFM has a period which we try to conjugate with the signal studied signal cycle duration, and with real studied signal and used mother wavelet. Hence, our basic difficulties are in this area, how to conjugate all these signals in one device.
Okay, thank you very much. We have no time for other questions, and the next 15 minutes also for you. We are waiting for the next presentation.
Yes, thank you. I will. Do you see the presentation?
Yes.
Yes,
yeah.
Yes.
Thank you. The next talk which I will present is a method of reliable electrocardiographic control of ischemia appearance investigations with experimental animals. We will, after short introduction, we will consider the problem statement, methodological, algorithmic, and hardware means for the stated problem solution, experimental application of the methodology, and some conclusions. The distinctive feature of ultra-high resolution electrocardiography method is comparison with other known ECG methods is a registration of electrocardiac signals in wider amplitude and frequency range, which has not been attainable for ECG before. Ultra-high resolution ECG provides a higher ECG amplitude and frequency resolution. The basic goal of the present research is to develop specific methodology of a reliable real-time ECG control for all experiments, for all experimental stages with test animals, especially ischemia stage, based on ultra-high resolution ECG method. Optical excuse me, please. I will, the problem to be solved is the following: fundamental functional ECG methodology development. It includes methods and approaches to studying of cardiovascular pathologies from the point of view of both physiology processes and technical support. Creation of artificial ischemia in experimental animals includes operation with experimental animals, detection of ultra-high resolution ECG signals during experimental stage, and their recording, and storage and data selection organization. The subject is to develop specific methodology and trustworthy ECG control for all stages of the signal investigation with experimental animal in real-time mode using new method of ultra-high resolution ECG, implementing continuous analysis of ECG signal components, high-frequency variation. High-frequency variations means studies in high-frequency signal got from high-frequency channel, which means signals between 100 and 2000 hertz. For a solution of the stated problem of real-time electrocardiographic control of the experimental stage with single animal, it has been proposed to use statistical and spectral characteristics of processed signals on the basis of theoretical approaches and previously acquired knowledge from the performed experiments, such as we use the methods of histogram plotting, method of spectral power density of high frequency signal components demonstration, and wavelet transform performance. This figure illustrates all the stage of both the experiment carrying out in the upper part of the figure and its ECG control in real-time mode, the lower. You see that the stages is preparation stage, stabilization stage, ischemia stage, and reperfusion stage, which are performed with the experimental animals. The experiments were carried out with outbred Wistar male rats weighing 240, 260 grams, cared by international regulation of standard diet. During the first preparation stage, the rat was brought to the state required for the experiment. Animal is drugged, then placed off a thermostatic operational table for keeping stable body temperature. Catheter is inserted into the femoral vein for continuous anesthesia maintenance. Artificial lung ventilation machine is connected to the tracheostomy, and animal is connected to a control cardiograph. The left anterolateral thoracotomy is carried out, and the pericardium is dissected for the left coronary artery access, and ligature is attracted for occlude formation that allows ischemia modeling. Then the occlusion is induced using the ligature inserted before to create artificial obstruction of heart blood flow. After the occlusion, the left coronary artery ischemia starts as it signed in the figure 1A upper part. And during the first minutes of the stage, high frequency signal characteristics are calculated periodically while the process mentioned above is carried out. They represent the ischemia stage conditions and allow to conclude by the mentioned earlier yes-no criteria that a pathology begins to develop. High-frequency channels provide extraction useful data or earlier annotatable for analysis on the basis of which, for instance, the real-time electrocardiographic control of the experiment is performed. The algorithm has been developed, which calculate the signal instant values hitting number to certain intervals of histogram curve formation. Here you see the histograms, which show the part of signal counts included in certain in certain compartment of voltage values. The A in the A picture is accords to stabilization stage. B accords to ischemia stage of 60 seconds, and the third is in accords to ischemia after 120 seconds. You see that the strong variation can be observed. Oh, excuse me. Excuse me. This picture shows the studies of spectral power density of the ultra high resolutions ECG signals with high frequency components. The first A picture shows demonstrates the stabilization stage. Second accords to ischemia 60 seconds, and the third ischemia 120 seconds. You see that high frequency components demonstrate very strong variation, and hence it can demonstrate that high frequency components are very informative, and it can be used for diagnostics of ischemia in more early stages than it is used in standard electrocardiographic mode. And at least we show the wavelet spectrograms which used without any acoustic devices, but in usual computer processing of signal in the stage of stabilization stage and ischemia 120 second artificial ischemia. You see that it has very strong variation. The pictures are very different, and it shows can produce many useful information of ischemia development. The approaches to elaboration of the second stage of consolidated basic excuse me methodology basic method of ischemia functional ECG is the method of reliable cardiographic control of all the stage separate investigation, all the separate investigation stage with experimental animals in real-time mode, as it was presented in this paper. It has been proposed to use statistical and spectral method, namely the procedures of the signal voltage instant values histograms formation and procedures of their spectral power density calculations. The algorithm and software has been developed which provide periodically real-time imaging of the calculation results at the PC monitor during all the experiment carrying out. In order to realize the information redundancy postulate accepted in our scientific school, in addition to two procedures, it was proposed to introduce also analysis of ultra-high resolution ECG signals wavelet spectrograms. Hence, the problem of experiment electrocardiographic control has been solved. Especially, it is related the most important moment, start of ischemia stage. It was made by means of practical realizations of the solution acceptance regarding ischemia developments start by yes, no criteria.
Okay. I'm sorry.
I see that it is the finish of my.
Yeah, so thank you very much. We have time for only one question, and the next speaker is Dmitry Teleshov with his big presentation. Because he is keynote speaker. Anton, I encourage you to ask questions.
Okay, Boris Simchovich, how big database you collected and by how much your proposal is better? You mentioned that you can measure this ischemia way in advance than other algorithms. Can you be more specific on this statement?
You see, the basic advantage of the proposed method is that the variations of electrocardiographic signals in higher obtained in the high frequency channels, which was not earlier accepted into consideration, allows to provide diagnostics of ischemia in more earlier stages of its development, because they appear earlier than the signs of ischemia, the signs of ischemia which appear in the signals recorded in the range of 0 to 100 Hertz. So this is my answer.
Anton, it's fine for you?
Okay, thank you.
Thank you very much. Thank you very much. We are waiting for Dmitry Teleshov. Are you here?
Thank you.
Yes.
I'm here. Hello. Hello, everyone.
Hello. We are writing your big presentation. It's very good that you join us. We are sorry for issues with organization, and we are ready to hear your perfect presentation and greatest ideas.
Okay, can you see my screen?
Yes, thank you.
Okay. First of all, I would like to say thank you very much for the inviting me to do the report during the this symposium, and thank you so much. And I would like to talk about artificial heart and the translation principles of artificial heart. our group working on the artificial heart more than 10 years, and it's one of our main topic of the research. And I'm right now sharing two positions in the Sechenov University. It's first Moscow State Medical University and National Research University of Miet, and it allows us to compare the technological and medical experience together. So, and the outline, I would like to little bit talk about the artificial heart and left ventricle assist device, the possibility of left ventricle assist device miniaturization and other application for the pediatric possibilities. And finally, I would like to share our results of the pediatric Sputnik left ventricle assist device. Okay, so I would like to start with this picture, which show us the clinical and technological way of artificial of the solving the problem of the heart. On the left side, you can see Professor Christian Bernard, who did the first human heart transplantation in the year 1967, and approximately after 1 year and a half was done the first implantation of the artificial heart. It's show that this technology are two different way of solving the heart problem was too close to each other on the way of more than 50 years. So, and of course, up to now, the heart transplantation is a gold standard for the patient with a heart failure. Heart failure is a serious problem when the heart cannot pass through the circulation system enough blood. It's quite dangerous, and it's not can be treated by the different pharma, and just the one case for such a patient is a heart transplantation or implantation of artificial heart. And here you can see just a few examples. On the left side, just a normal heart. On the central is a artificial heart, and the idea is just quite obvious for the engineers. We should repeat the heart possibilities for blood transferring, and here is a system which allows to to model left and right ventricles with 4 valves, and allows to passing through the blood through the systemic and pulmonary circulation. That was the idea, and I would like to say that till now the total artificial heart looked like this one. During the last 50 years, there is not so much progress in the technology, because just the two chambers which with the valve is allowed to pass in the blood through the heart. Another thing what I would like to talk a little bit more, it's ventricle assist device. It's this one is a more preferable system, and in majority cases it's used for the patient with a heart failure, because for the majority patients they have left ventricle heart failure, not the whole heart failure, but left ventricle. That means it's not necessary to remove the whole heart. It's just possible to carry out the blood from the left ventricle to the aorta with a heart pump. This idea was realized more than 10 years ago, and now the majority of artificial hearts are left ventricular assist devices. And I would like to say that during the last 10 years, we can see more left ventricular assist device and the heart transplantation in the world. The reason for that, of course, that donor shortage. There is no significantly rising of the heart transplant, but of course it's possible to produce a lot of left ventricular assist device. And one of the last report concerning the LVAD implantations shows the recent data, how the technology developed. Here include a majority implantation from the American hospitals. And during the last 10 years, we can see the rising of the implantation of the year 2019 was the highest amount of the implantation, more than 3,000 implantation in the US, and but I said that technologically it's changed, not and here represented three devices which go one go after another in area of implantation. Firstly, is here is a HeartMate 2 pump. It's up to now it's most implantable pump, and majority patients has such a pump in the world. It's the axial flow pump, and it was FDA approved in the year 2009, and after that there was high rising of the such pump implantation. And the blue bar is application of such a pump during the years. It's the axial flow pump, and the next one is a centrifugal pump. It's a hybrid hydraulic and magnetically levitated pump, and here it's possible to see how it's this pump was also involved on the market, and the red bar is the application of such a pump. And the next third one is a HeartMate 3, is an absolutely magnetically levitated pump. It's right now it's more implantable pump during the last 2 years, especially the years 2018 and 2019 when it was approved. So this technology improves the 1 year, 2 year survival of the patient up to the more than 80 and 70% respectively. It's become more and more close to the result of the heart transplantation. But we have a lot of problem after the implantation. Is such a problem like stroke. We can observe there is a slightly go down of the stroke incident, but it's still high problem. And another thing is the bleeding. It's caused by the hemolysis of the pump, and we will talk about it a little bit later during my talk. And so another important thing, it's just at the beginning, since the year 2015, it was a temporary use of more circulation system, and up to now it's a destination therapy, and about 73% in the year 2018 received the pump as a destination therapy. That means that patient will not receive the heart transplant. That means that they will live under the what support the whole life. This is a major trend because of the donor shortage, as I mentioned before. So it's just an illustration of the various left ventricular assist device application during the last 30 years, and one of the first application of our pump is called Sputnik Watt, and of course Sputnik is very familiar right now because the Sputnik vaccine, Sputnik V or Sputnik 5, but in the year 2012 was the first implantation in human. The Sputnik Watt is a Russian ventricular assist device. So with the axial flow pump, and here represented the variable components on the left and the control unit with the pump on the right. And briefly about the principle, how it's works, is just the majority technologies in the era of left ventricular assist device come from the aerospace, and here is a turbo machine, which includes the rotor with permanent magnet with the blades, and the stator with electromagnet. And it's allowed to generate the flow up to 10 liters per minute, and with this speed about 10,000 revolutions per minute. Okay, I would like to talk a little bit about the miniaturization. Why miniaturization is important here? Just first application of the Sputnik Watt in the of the pediatric application for the 15 years old patient. Here, this operation was done in the St. Petersburg in the Almazov Center, and of course, it's great that this patient is suitable for the application, but majority of the pediatric patient can be treated with the left ventricular assist device because of a few reasons. Firstly, this technology developed firstly for the adult patient, and another one because of the size of the pump is not possible to implant it in the small body. Here is presented the progress in the miniaturization, and I would like to show you another picture. The first pump was more than 1 kilo, and now the pump about 100 or 200 grams. So the size has reduced significantly, weight was reduced significantly, but and power consumption as well. But we have the parameter which should be stable. It's the flow that the pump should generate. So he just visualization why it's we still have the problem of the pediatric watt implantation, because on the right is a clinically approved pump, but it's not possible to apply them for this small pediatric patient. And on the left and the bottom side are the pediatric pump, but they are still under development. It's not applied not, there is no application as a clinic. It's of course miniaturization has some advantages. It's less invasive therapy, treatment of patients with non-standard cardiac anatomy. It's a possibility of right and left ventricle support when you can implant the 2 devices in one patient. Reduce the cost of surgical procedures because it's less invasive to improve patient outcomes and quality of life, because it's once again less invasive. That means that rehabilitation can be not so long. So also we have technological process or this way. Of course, we have the computational engineering tools which allow us develop the pump, and of course we can use new materials. Here, just an example from our lab, and just the pump under the modeling process, and rotor under the production, and the new materials. It's application of the ceramics, because ceramics quite biocompatible materials, and one of the idea to apply the ceramics for the left ventricular device. So and the importance of the pediatric application is shown here. We can observe, especially in the US, rising of the cases of application of the left ventricular assist device on the pediatric patient. But of course, this device was developed for the adult patient. And this is not a good idea to apply the device which was developed for the adult patient in the pediatric, because the pediatric patient is not just a smaller adult. But nevertheless, it's increase the patient survival, and it's just one of the papers illustrated the main message of the paper is irrespective to other factors, pediatric patients supported with the VAC were 4 times more likely to survive to transplant. That means that this patient have 4 times more chance to receive the heart transplant in the waiting list. So few words about our project of the pediatric Sputnik LVAD. Of course, this project have started with the criteria, firstly the anatomical fit, physiological, biological, psychological requirements, performance, biocompatibility, reliability, of course, manufacturability is very important, but you can produce the device what you develop. So why is pediatric is not small adults? Because for the adults and the pediatric patients have absolutely different operating range. If in the pressure which should be achieved, there is not so significance, but there is a high significance in the flow rate which should be generated in the pump. So another criteria is, of course, is a body weight, and in our study we hope to develop the pump for the patient with more than 12 kilo. One of the problems when you try to miniaturize something in the artificial heart is the hemolysis problem, because of the high shear stress, which caused by the very small gaps inside the pump. And what we can observe, the rising of the hemolysis depends on the 2 parameters. Is a shear stress, and another is exposure time, is the time which erythrocytes stand under this high shear. And of course, if you increase the shear stress, you should reduce the time under this shear. And one of our idea was, okay, we can improve the shear stress, because it is impossible in the small pump to increase the gaps inside, but we should try to develop the profile which allow to reduce significantly exposure time. It means it's finally should be beneficial for the hemolysis. It's just a principle constructed scheme of the pump. It's axial flow pump, it's the same principle I showed you before the Sputnik pump. On the first stage of the development, we did the MRI study of the patient with the health failure. It's a 4 years old child, and we investigate the fit of the pump and how pump will fit inside the patient. That it is possible to observe for 4 years old patient is okay. It's for the implantation. Another one is modeling of the flow behavior, and here it's possible to see the different flow profiles on the right, and on the top with the 1 liters per minute, and in the middle 3 liters, and the bottom is 5 liters per minute. It's possible to see significant difference in the flow profiles. For example, here the 1 liter per minute, we can observe the lines of flow stagnation and the recirculation. It's quite bad for the pump application, because that can be the reason of the thrombus formation. Because if we have there is no flow inside the pump, that can be the reason of thrombus formation. This is another reason why it's impossible to use the adult pump in the pediatric, because the different operating range with the different flow which they should generate. And in our study, we compare pediatric watt and adult watts, Sputnik adult watt, in the same operating point, with a generated flow 2.4 liters per minute with the pressure head. Pressure head is a difference between pressure inside the left ventricle and aorta, and it was a little bit more than 70 millimeters of mercury. And of course, the pump has different speed. For the smaller pump, for the achieve the same flow, we should increase the speed, and the speed for the pediatric pump was 12,000 RPM per minute, revolution per minute, and for the adult ones 7,000 revolution per minute. And it's possible to see the different in the flow profile, and the main point of this picture is almost in 5 times difference in the residence time. For the pediatric one, it was 89 milliseconds. For the adult one, it is 385 milliseconds. That means that the platelets spend significantly more time inside the pump. But it's very bad for the hemolysis, and very good for us. What we reduce this time significantly, and this is was the idea by increasing the hemolysis, because we can not decreasing the hemolysis, because we can not reduce the shear stress. So it's some prototyping of the pump. Here just photo of the different stages of the prototyping here, and here just mock circulation loop study, because we should before the animal trials we should investigate how the behavior of the pump in the model condition, and we generate the pediatric patient with a heart failure. So here the results received during the mock circulation loop study, and on the left is pressure volume loops of the left ventricle, and we can see unloading of the left ventricle. That means we can observe decrease in the size volume of the left ventricle and the pressure inside the left ventricle under the pump support, and with increasing of the speed of the pump, of course. And on the right side is a pump profile, is the flow rate and the head pressure of the pump, and it is possible to see that the pump transfer not the constant flow, it's also pulsatile flow which pump generate. So this is a flow behavior, and we can see that there is a increase in the flow, total flow, with the rising of the speed of the pump. This is the major idea to increase the flow, total flow of the patient. Here, results of the hemolysis of the pump. It's on the top. It's a hemolysis caused by the pump. On the bottom is a self hemolysis, because you know, in the all human have the self hemolysis process, and we can see that our conception of the pump miniaturization was quite good, because we didn't observe significant hemolysis inside the pump, and finally NIH index of the hemolysis, the standard index of the hemolysis was in 2.5 lower than for the pediatric, when for the adult pump. So this is there the comparison of the size of the pump. It's less than 100 grams, and we can observe significant reduction of the size, pump size. So, and in the conclusion, I'm just the few message. Miniaturization of the VATS can be of important benefits, including less invasive implantation techniques and more versatility in patient selection. One of the problems caused by the VATS size reduction is the risk of the hemolysis and thrombosis. And but the blood thromba depends on both shear stress and the resilience times, and the reduction of the resilience times during the miniaturization can decrease the hemolysis potentially. And just the LVAT miniaturization is not enough for the pediatric patient, because the difference in inspiration range in compared with the adults LVAT. So this is all what I wanted to present it today, and thank you for your attention, and thank you for inviting me to do my report. Thank you very much.
Thank you very much. It's a great presentation. We can shift our the following presentation a little bit, and we have about 5 minutes for questions. First question from me: what computational software do you use for design this device?
It's just classical engineering software. We used ANSYS firstly, and also some colleagues of mine apply COMSOL. It just quite good for the CFD analysis.
Thank you. Other questions?
So my question may be a little bit out of scope of the presentation itself, but can you please elaborate on how many, legal procedures you need to pass so your product, these VAT systems are allowed to be used in wide practice? So. Yeah.
Thank you very much for this question. It's a very important question. For the adult VAT, it's already on the market, and it was firstly implanted in the year 2012, and up to now we have more than 50 implantation in human. I would like to say it. We were quite lucky in that time, more than 10 years, about 10 years ago, because the regulation was not so strong like we have right now, and now it took significantly more and more time for the registration of such device, because this is a third class of the risk of the medical device, which is the highest class of the risk, and of course it took in general more than 2 years just for the registration. It's a long process, yeah. So it's a long process, but it's a long process everywhere, and it took a lot of time, unfortunately.
Thank you. And do you operate only on a Russian market, or you try to expand globally with your solution?
We are working on the Russian market with Sputnik V. Globally, it's also quite complicated, because you should certificate your pump according to the European and US standards. But it's quite expensive, and it's quite competitive market right now. And another idea to what we have right now, and we are talking with our colleagues from the India, because it might be more beneficial for us to go on this market, because in the developed countries the price of the cost of the pump is not so important, because the insurance covers the implantation. On the emergency market, it's the cost is makes sense, and of course it should be decrease significantly for the application. And in general, for us, it's not the priority go to the European or US market, but we are we hope that it will be applied in the India market.
Thank you. It's very interesting. Any other questions?
I think we have a question in chat. What are the main reasons for such a long development of the prototype? It seems that the project has a huge potential for investment. It's from Vladislav Proskurov.
I hope I understood your question clearly. You know, it's unfortunately in Russia we have not so high potential for the investment and in the field of different medical equipment projects, because we are quite lucky with the pharma, and we have few pharma giant companies, and other results of such a potential was vaccine, Sputnik vaccine, but our potential for the medical equipment market is not so high, and there are not so there are no big companies, Russian big companies on this market, and we have not such a giant like Medtronic, General Electric, or Philips and Siemens as well, and it's still a problem for the people who would like to translate the results in clinic, because you should try to receive investments which needed for you, but it's quite complicated process, and of course it's quite long process. Why IT is compared with the IT technology? Of course, any IT product can be developed during 1 year, but for the medical equipment, it's not true. It's 5-10 years for the development, and during this period you have only expenditures of the money. Okay.
Thank you very much. We have no other time for questions, and we have no questions. I'm very glad that this presentation was shown. It's very interesting topics, and where I wish you luck with foundation and for goes to Indian market. I hope we make a great product, and this product goes to other countries and will be yes, it's really look very good, and it's really great. We wish you hope, wish you luck, and we ask about other speaker. Other speaker is Handavi Suleiman, study of the ventricular late potential characteristics of the patients with heart conduction way abnormality.
Hello everyone. My colleague Darina Rybka will do the presentation with the name of our supervisor Zafar Yuldashev. She will share and she will present this study.
Yeah, that's me.
Okay.
We don't hear.
I'm here.
Your microphone is too. Something goes wrong, and your speech is very is insufficient volume.
Okay, 1 minute. I'll try to do something.
Not yet.
And now, can you hear me?
Unfortunately, it's too quiet.
Well, I can't do anything for better.
Previous time I hear a good speech and with loud enough.
Previous, yeah, not now.
But not now, yes.
And now, is it better?
No.
No. I don't know what is the reason of this.
Nope.
Sorry.
Maybe Hanadi can make the presentation and you will be switching the slides because her microphone is definitely working better.
Okay, I will make it.
Okay, perfect. Let's start, please.
Darina, you may stop sharing. Our paper is the study of ventricular late potential characteristic of the patient with heart conducting ways abnormality. First of all, we know, all of us know that late ventricular potential, VLP, are a significant sign of heart conducting pathways disorders. So they are caused by structural or morphological changes in the ventricular myocardium, and they are a good predictor for sudden cardiac death. The method that we will use is the technology of high-resolution ECG to detect VLP signals. Known methods are using detecting VLP based on the registration of surface ECG. In the general accepted practice, VLP are assessed by the orthogonal leads, X, Y, and Z. To achieve this goal, we had to formulate a database of synchronous recording of intracardiac electrograms and 12-channel surface ECG signals reflecting the ventricular tachycardia and abnormality of conducting ways. Second, we had to detect these VLB signals and allocate them, their characteristic in time domain and with the intracardiac electrograms abnormality, and formulate the complex of indicators of their characteristics that reflect the location of intracardiac disruption, area, and degree of abnormality. The database that we used is a Cronus recording of 12-channel ECG, surface ECG, and intracardiac electrograms. We recorded it with established morphological disorders of the ventricular myocardium. This ECG were registered by a sampling rate of 1 kilohertz and a resolution of 24 bits. A delay in the process of ventricular depolarization and the presence of late ventricle potential were a result of these recordings. So first of all, we have the point detection. To detect the ECG signals characteristic, we need to detect the points QRS on, QRS off, and the G point against the background of the interference and noise. So we added the module that provided the selection of the largest signal between 12-channel signals, which is characterized by the highest signal-to-noise ratio. There was no potential in the section with the G point. Therefore, to identify it, we took a time window of 10 samples to detect it. The characteristic of VLB, to identify the relationship between the characteristic of VLB and the intracardiac electrograms with the orthogonal ECG signals, with the place of the localization and degree of the morphological changes in the myocardium. It was advisable to use the ratio of levels of orthogonal ECG, the power of intracardiac electrograms, the time domain of VLB appearance, and the QRS complex duration, root mean square voltage of the terminal in milliseconds of the QRS complex, and the amount of time that the complex remains below 40 microvolts. This graphs show our results of detecting this. We can see that we detected for 3 patients as a sample of our database, and we can see that in the third graph we had detected the G points in the vector magnitude, and we can see where we can find it for the ventricular late potentials in the 4th row. Those patients were taken for different disorders. So as you can see, they are like, we have different shape of the ventricular vector magnitude and the VLB. So our conclusion is that the detection of VLB signals and studying its characteristic is assessing the ratio of the power is by assessing the ratio of the power of the orthogonal ECG signals component will make it possible to assess the degree and localization of the area of the heart conducting pathways and abnormality, and determine the risk of further diseases exacerbation. Further development of this technology and improvement will increase the quality of medical care out of the clinics. So our main goal is to improve a telemedicine system that will make us able to detect and diagnose disorders, cardiovascular disorders out of the clinic. Thank you for your attention.
Thank you very much. Any questions from non-chair member? Okay, I have questions about your results, and usually vector cardiographs are presented in 3-dimensional space, where how the vector draws the line in 3D space. Could you show these results? And also, I don't understand what group of patients do you study? How much people? How much
Okay.
people provide the data for this study? Yeah.
For your first question, we have the vector magnitude. The vector magnitude is the magnitude of the 3 orthogonal leads. So instead of showing the graph of the 3-dimensional of the orthogonal leads, we used 1-dimensional, which is the vector magnitude. And you can see it here in the graph. As for your second questions, nowadays we are preparing a database at Almazov Center. This database has a plenty of different cardiovascular diseases. Mostly we have ventricular tachycardia, different type of arrhythmia, like ventricular tachycardia, and atrial fibrillation and flutter, and also like this database is being now prepared, so, and we will be published in like 2 months from now. The second month it will be ready and we will publish. As you mentioned, like what recording do we have? Until now, the recordings that we have is mostly detect, our main focus is to detect VLP. Also, we have fragmented potential. We have different morphological of VT, ventricular tachycardia. So until now, this is our main focus. This month and the rest of this month and next month, we will expand this database, and the first version of it will be published like in 2 months.
Thank you. And one more question. Why these effects and some changes appears on ECG in this time? How you explain it from physiological point of view? What's happened in heart, which produce these changes on ECG?
Okay, so the VLPs are generated by morphological and spatial destruction of the conducting ways in the heart. So if we had a patient with a recent stroke or with a recent myocardial infarction, this will show on the VLB, on the shape of the VLB. By examining the characteristic of the LB, domain characteristic, the time domain characteristic, we are trying to differentiate, let's say, from an engineering point of view, how to differentiate this disorders using those characteristics.
Okay, I don't agree. From my point of view, it's not enough for explain what happened. Okay, maybe any other questions?
So my question, maybe I didn't quite get. Have you done, say, maybe some sort of comparative analysis with other research groups of your algorithms, of your predictions, and how they work on, not only your data, but like open database data, something like that? Have you done it?
Unfortunately, in the other available databases, we don't have the VLB doesn't exist, because they're like the most common one, used one database. It is BTB, and it has 16-bit of registration. So this was not enough. We couldn't see any VLB signals in that database. That's why we are trying to, we are preparing our own database that has 24 bits of registration that will make us detect and see the VLB signals more accurately.
Okay, thank you.
Thank you. We are writing full publication from your group. It's very interesting topics, but we want to understand more about what happened and how it will finish. Okay, the next presentation is presentation of Anastasia Plitenkova, processing of heart rate signals using digital spectral analysis on the plane of complex frequencies when estimating the reactivity of regulation mechanism of the heart of the human. Are you ready?
Yes, I'm ready.
Okay, let's start.
Just a second. Please. I have a problem. I don't show my screen.
Okay, we have 1 minute for. Could you try again or make something other? We have 2 minutes for fix your problem.
Reconnect is not the only way. Life is life.
I suppose it's Mac. On Mac, yeah, Zoom sometimes can't obtain image from the screen, and for this reason you need to restart them. Dear friends, maybe we discuss about previous presentation or something. Oh no.
Do you hear me?
Yes.
Yes, we hear you.
Have you fixed your problem?
No.
You can send presentation to me. I show on my screen. You will comment and speak.
Well, I can do it.
Yes. Oh, Andrei. Oh, screen.
Yes, thank you.
Perfect. Okay. Let's start.
Good afternoon. My name is Anastasia, and I'm a student at the South Ural State University. Today, I'm going to tell you about processing of heart rate signals using digital spectral analysis on the plane of complex frequencies when estimating the reactivity of regulation mechanism of the human physiological system. Next slide, please. Topical issue is identification of transient oscillation structure parameters in the frequency domain reflected by the time dependence of HRV arising under the influence of various functional tests, for example, when assessing the reactivity of regulation mechanism of the human physiological system. Next slide, please. It's possible to assess the functional state of a person using the classical spectral analysis of the heart rate. Spectral analysis involves the decomposition of the time dependence of heart rate and variability HRV into separate rhythms with different frequencies and an assessment of their intensity. The dependence of the estimated intensity on frequency is set by the calculated dependence of the spectral power density, PSD, of HRV on frequency. To calculate the HRV PSD, the Welsh periodogram method is currently used. Next slide, please. The action of regulation mechanism in the human body during heart rhythm recording must remain constant. In this case, the conclusion based on the analysis of power spectral density, PSD of HRV, can be considered correct. Otherwise, HRV record will reflect different transient processes corresponding to restructuring of regulation systems. And for this case, the model of decomposition of HRV record on constant rhythms is inapplicable. That is, the classical spectral analysis of the time series is applicable only if the processed time series is stationary. To analyze the measured signals reflecting transient processes, it's proposed to use the technology of digital spectral analysis on the plane of complex frequencies, SCF. Next slide, please. The aim of the work is to determine the capabilities of the method of digital spectral analysis on the plane of complex HRV frequencies for assessing the reactivity of various mechanisms of heart rate regulation in response to functional tests directly from the data of non-stationary heart rate records. The SCF method was for assessing the reactivity of the mechanism of regulation of the human physiological system is implemented using the PRONI parametric model. Next slide, please. Currently, 4 regulation ranges are distinguished. These ranges are shown on the slide. HRV transients are usually excluded during spectral analysis. It's possible to note that during action of functional tests, transient process should reflect rearrangement of oscillation frequency structure of a heart rhythm within generally accepted frequency ranges ULF, VLF, LF, HF, each of which separately will reflect reaction of the corresponding regulatory mechanism of human physiological system. Calculation of numerical values of parameters of reactions of various regulatory mechanisms of the heart rhythm during immediate influence of the functional test or after leaving it will increase the number of informative parameters for more precise diagnostics of regulatory mechanism of physiological system of the person. Transients of cardiac rhythm are non-stationary process. Next slide, please. Spectral analysis on the complex frequency plane using the PRONI procedure approximates the sequence obtained from the process samples by a linear combination of attenuating, increasing or constant amplitude cosine waves. During the study, parameters were developed for a generalized description of the non-stationary transient process reflected by the observed time series using the spectrum on the plane of complex frequencies. The parameters can be calculated separately for the generally accepted frequency ranges. Next slide, please. In Fig 1 shows the dependence of HRV in a transient non-stationary state. Fig 2 shows the corresponding dependence of the HRV PSD in the range of 0 to 0.5 Hertz. The transient process reflects a person's response to stress, mental counting with a time limit. The concentration of the spectrum in one low frequency peak is due to the tendency for the average RR intervals to decrease over time. In this case, non-stationary processes, the classical spectrum, Fig 2, has lost its information content. Next slide, please. Fig 3 shows the protocol for spectral analysis of HRV recording. Fig 1 on the plane of complex frequencies. The calculated values of the parameters for the generalized description of the non-stationary transient process using the spectrum on the plane of complex frequencies are shown in table 1. Next slide, please. The table on the previous slide shows generalized parameters reflecting the SCF structure as well as separately by characteristic frequency ranges. They are described on this slide. Usually these parameters are used to interpret measurement results by medical professionals. Next slide. Fig 4 shows the dependence of HRV in a steady state, resting state. In Fig 5, the calculation was performed by the Welch periodogram method. Fig 5 that the regulation of HRV is most pronounced by the spectrum peaks in the VLF and LF frequency ranges. The frequency of the maximum spectrum peak, FP, equals 0.00244 Hz, is in the ULF range. It can be assumed that the activity of the HF range is determined by random chaotic fluctuations in a HRV. Next slide, please. Fig 6 shows the protocol of spectral analysis of HRV recording. Fig 4 on the plane of complex frequencies. The calculated values of the parameters for the generalized description of the stationary process, Fig 4, using the spectrum on the plane of complex frequencies are given in table 2. Next slide, please. It can be seen from the table that is in the ULF range, CIR equal 0, which indicates the presence of one harmonic with a sufficiently stable amplitude in time. In the ULF range, the dynamics of the analyzed HRV record is stationary. Therefore, the lowest frequency peak of the spectrum Fig 5 should be included in the assessment of the INS state. Next slide, please. 3 types of the state of transient processes of change in the heart rate in school children during the correction test were investigated using the SCF method. Using a representative sample of data, it was shown that a reliable connection was revealed between the features of dynamics of the heart rate and the indicator of concentration of attention when performing a correction test in school children, which is important for determining the level of functional tension of the child's regulatory systems, which is determined by the degree of physiological maturity of the body and environmental conditions. Next slide. The SCF method was used to study the scheme for the implementation of autonomic support of adaptive hemodynamic reactions associated with aging through the assessment of the variability of hemodynamic parameters. It has been shown that the heart rate increases significantly with age, and using the SCF method, it has been shown that this process is accompanied by a decrease in the stationary component in the higher frequency ranges of heart rate variability, which indicates a weakening of autonomic bar and volumetric regulation. Next slide. Spectral analysis on the plane of complex frequencies has been introduced into clinical practice as a new method for assessing the variability of the hemodynamic parameters of the human body. It's shown that the results obtained in the course of clinical practice are the basis for the practical use of the fluctuating vibration model of blood circulation developed on the basis of the original technology using spectral analysis on the plane of complex frequencies to assess the probability of an unfavorable prognosis. For example, in the course of clinical practice, the prognostic significance of a comprehensive assessment of the stationary component of the variability of a number of hemodynamic parameters has been proven in order to identify patients with a high probability of death in traumatic brain injury. Next slide. The addition of the SCF method to the classical spectral analysis provides more complete information when assessing the regulatory processes of the heart rhythm, especially in terms of non-stationary transient processes. Using the SCF, it's possible to establish the non-stationary nature of a part of the investigated HRV process corresponding to the frequency range of the spectrum that is significant for diagnostics, which will eliminate errors in the physiological interpretation of the peak activity of the corresponding frequency regions in classical spectral analysis. Next slide, please. The SCF method makes it possible to accurately identify the transient processes of HRV with an assessment of the reactivity of the mechanisms of regulation of the heart rhythm separately according to the generally accepted frequency ranges. The addition of the SCF method to the classical spectral analysis allows for diagnostics based on short-minute HRV records, since there is possibility of more accurate in comparison with the classical method identification of the frequency components of the heart rate. Thank you for your attention, and now I'm open for your questions.
Thank you very much. I want to ask you about maybe other questions from our guests. Okay, I have one question. You propose some estimations, you propose new methods and new metrics for error interval series, but error interval series about 58 already error series can be processed as 58 different indexes. And from this point of view, maybe introduced results is very close to something old than you propose. I ask it because for many diseases and for normal heart, some metrics strongly correlated with each other, and for these reasons, parameter space may be reduced to a very small number of components. Maybe you try this analysis and compare proposed metrics with something proposed before.
We propose a classical method to apply it with a method based on the spectrum on complex frequencies.
But you process error interval series. Are you process error interval series? Yes?
Yes.
58 different indexes already exist for this series. Do you compare your indices with proposed yearly? PNN 50, RMSSD, PNN 20, many others. HV, for example, if you must talk about spectrum of error interval.
I don't know.
Okay, thank you.
My question may be about, well, this statement, you mentioned a representative sample of data. How big was this sample? Because from the presentation, it appears that you show just, couple examples.
It's difficult for me to answer this question. Sorry.
Okay, I sent you some review in chat. Maybe you answer in discussion after the main section or in chat for my questions, because it's very interesting for me. And currently we go to the next presentation. It's the last presentation in this block. Andrei Brico, amplitude parameter of electrical impedance myography with different pressure of the electrode system research.
I speak this presentation.
Okay, thank you. Well, let's share your screen and let's start.
Okay. Do you see my presentation?
Yes.
Good afternoon, dear chairman and participants of the conference. My name is Kapravchuk Vladislava, and I want to introduce our study, amplitude parameters of electrical impedance myography with a different pressure of the electrode system research. Bionic control systems are implemented by a neuromuscular interface, which is an intermediate link between the body and the equating mechanism. The key moment is the choice of a method for obtaining information about the movement performed by a limb, which makes it possible to determine its type and perform a numerical estimate of the force moment characteristics. Electrical impedance myography is a promising concept, but requires further study methods. The purpose of this research is to study the influence of amplitude parameters of electrical impedance myography at various pressure of the electrode system to the skin surface. Electrical impedance measurement is a non-invasive method for determining the electrical properties of tissues. This method consists of placing a high-frequency probing current between current electrodes and rejecting the arising potential different at the measuring electrodes located in the projection area of a muscle or muscle group that are active during action. The measured values of electrical impedance carry information about the electrical properties of biological tissues at the depth of probing. Muscle contraction leads to a change in the electrical impedance signal. This is a consequence of morphological and electrophysical changes in the parameters of the sensing area. Uncontrolled pressure of the electrode system has a significant effect on morphological change associated with motor activity. It can also lead to errors in recognizing the type of the action and a decrease in the quality of proportional control. Stable contact of the electrode system with the measurement area can be achieved due to defined pressure force of the electrode. In case of insufficient pressure, there may be distortion in the position of the electrode system associated with thicknessing of the muscles during construction. This can lead to adverse artifacts or complete loss of contact of the electrodes with the skin surface. Excessive pressure is unacceptable, as well as it also leads to distorted result, discomfort for person, and the inability to use the system for a long time. Thus, an important task it is to determine the acceptable contact pressure of the electrode assembly, and it is allowed to carry out measurements that are comfortable for the volunteer with sufficient accuracy to generate control commands for the executive device. To control the displacement and pressure force of the electrode assembly to the skin surface and register electrical impedance myography, a laboratory test stand was assembled. The laboratory complex included a pressure stand, a status side device for bioelectrical measurements, and a mechanical signal conversion device. The pressure stand included stepping motors for precise positioning of the electrode system in the horizontal plane relative to the measurement area, and for vertical movement in order to realize pressure. The pressure force value was recorded using 4 sensors. An optical encoder was used to measure the vertical displacement feedback. The electrode system was installed by means of special fasteners on a construction with 4 sensors. The electrodes, the form of a circle with a diameter of 7 millimeters, were equidistant from each other by 10 millimeters. To perform the action with the force, a wrist expander with a preset load of 10 decanewtons was used. The technical characteristics of the complex are presented in the table on the slide. To determine the dependency of changing amplitude parameters of electrical impedance myography on the pressure force of the electrode system during the grip of the wrist expander, measurements were made on 10 healthy volunteers. The object of the study was the upper third of the volunteer's forearm with a girth of 20 to 35 centimeters. The volunteer forearms were positioned in the pressure stand. Then the operator positioned the electrode system by pressing it to the skin until contact appeared. Before the measurement, contact electrode paste was applied to the electrodes to reduce the electrode skin resistance. The recording of the electrical impedance signal was consistently carried out in the area of projection of the antagonist muscles. During the measurements, the volunteers circularly performed the grip of the wrist expander, after which the electrode system pressure force was iteratively increased. Example of the signals measurements in a single study is shown on a slide. Analysis of the absolute values of electrical impedance shows that when the pressure force is in the range of 0.2 to 0.5 decanewtons, the dependence of the amplitude of electrical impedance on the pressure force reached a plateau. The parameter delta R was investigated. It was calculated as a difference between the electrical impedance at rest and during action. The delta parameter reflects the change in the amplitude of the action pattern in the electrical impedance signal. At low electrode pressure forces up to 0.2 decanewtons, high values of the parameter delta R are observed. However, the signal is unstable at the slightest change in the pressure force of the electrodes. In order to avoid signal instability, the pressure force of the electrode system must be in the range from 0.2 to 0.5 decanewtons. In this range of pressure force, a pronounced and reproducible change in the signal is observed when performing actions. A further increase in the pressure force leads to the fact that the parameter delta R is extremely small values. As a result, it is quite difficult to identify movement patterns. The process of using devices such as prostheses, ortheses, bracelets to control devices in everyday life has one important problem for developers. It is constant change in the pressure force of the electrodes during the use of the device. The electrode system pressure force can influence on the electrical impedance signal and the action pattern in the signal. To ensure proportional control, it is necessary to work with a stable signal, the change of which will slightly depend on the electrode system pressure force when performing action. As a result of the research, it was determined that there is a range of electrode system pressure force at which a stable contact of the electrodes with the skin is ensured, discomfort does not arise, and a stable electrical impedance signal is provided. Movement patterns in this range do not depend on the electrode system pressure force. For healthy volunteers, the range was from 0.2 to 0.5 decanewtons. Designing control systems based on this result will provide proportional control, prevent the formation of erroneous commands, and improve the quality of device control. Thank you for your attention. I'm glad to answer your questions.
Thank you very much. How you perform statistical analysis in your study? You have 10 volunteers, it's a small group, and you use methods of ECG processing, or sorry, not ECG, but impedance processing. Why do you analyze sensitivity and some statistical properties of your approach?
We will do this in future. In future for more volunteers, and for this research we analyze these signals with MATLAB, and when the signal is good.
Okay, thank you. Maybe other questions from our colleagues? Okay, in this case, we go to some break. If you want, we can discuss something. Anton, are you ready for discuss something? Maybe you want to you take participation. I propose to. Okay, I start screen. Sorry. Yes, start screen with break. But maybe we want to discuss some topics. Anton, you have a discussion on round tables about ophthalmology. Maybe you explain, maybe you say something about this event and what's happened, what's result after.
Well, this event was quite interesting. Well, it was, people of a very, different topics, different specialization, I must say, but, this topic of, ophthalmology and biomedical engineering is, by design multidisciplinary, so it was very nice. So there were guys from Bauman Institute who were doing the modeling of the blood in the eye, and photoplethysmographs to track this high blood pressure. There was also presentation by our Yekaterinburg's eye microsurgery representatives who were solving the issue of using the physiological system to track the toxicity of the drug that is inserted in the eye. So, and this electrophysiological signals are like, the main way to track the toxicity in the eye. So you can balance the number of drug you introduce to patients to, specific features of the patients, because some patients might be more resistant to drugs, some are less. Also, there was a very nice talk from Moscow, guys who were, let's say, reverse engineering the databases of the interfaces for capturing the data, electrophysiological data, because unfortunately the developers was not so eager to make a system that is able to be interact in the future for the long-term processing. So they save in a very weird old school Delphi format. So these guys in Moscow actually spent some time, like maybe half a year, to decode it in some weird way and use it in the future. And I think the last presentation was done by Ukrainian scientists. They are working on real life application of deep learning of these OCT images, and they have actual practical applications. So they're more focused not on this publication of good results of accuracy, blah blah blah, but they more work with real life data. And for the last 3 years, they are successfully working with like 3 companies and plan to move on. And the main aspiration for them was that in 2018, FDA, the American company that regularize everything that is basically happening in the healthcare, this FDA approved artificial intelligence system for wide clinical application. So yeah, it was fun and nice to see different people together sharing their ideas. And next year we want to invite more colleagues and to work together.
Excuse me, why is this event named round table, but not usual section? Because you speak about presentation, it's look like presentation, like usual presentation conference.
Well, it's it was just the wish of the guy who kind of came to all these people and talked to them.
Okay. Interesting. And what do you think about this practice? Do you repeat it in the next conference?
For sure. This year we want. It was held in Russian-speaking format only because, unfortunately, our colleagues from the other countries did not able to join. But next year we want to meet together to share our progress for this year, how we kind of move with our investigations, and ask for new colleagues to join. So yeah.
Dear colleagues, maybe we discuss some presentation in our section and something about ECG processing, about signal processing in general, because our topics was very narrow and very close to signal processing. The previous block first block in my section was about image processing and about segmentation problem. The second is generally about processing of signals, and here we can find some specialists in these topics. Okay, people goes to his presentation, show something, and turn off, and stay in online only for view. Okay. Anton, maybe you have finished full paper about your recent studies?
Not yet. I'm, in endless stage of maybe I should do this, do that. Plus, I'm preoccupied with bureaucratic issues related to the study process. So I'm trying to squeeze the science in my timetable, but unfortunately, that is not always the case.
Okay, I want to show my last publication if it's possible. Sorry.
EGM one or
in PLOS one?
Oh.
Okay, I sent in chat. I use my position of co-chair for push my studies.
That's fine, you know.
This is my last work. It's performed with on data of commercial company. It was Russian startup and then startups from Switzerland. And this is computational modeling of the real ECG. It's we take a very well-known approach for simulation of ECG and repeat on complex cases. People have different disease, and we have all very heterogeneous set of diseases. And currently, we make simulation with B-domain model of ECG of these patients. And we study how parameter change, how close we can repeat real ECG, and can be possibility to improve this fitting using changes of some parameters and fine-tuning model for real data.
It is for adults only model?
It's for adults, yes, because this idea of this study, it's people with point stimulation. Some people have CRT devices, cardiac resynchronization therapy devices, and some other have ectopic focuses, and all of them pass through ablation. I know about some works, about 2 or 3 works performed on these topics of study on children, on pediatric data, but it's very complex because pediatric cardiology is not about electrophysiological problem, because electrophysiology very important to aged patients, and yep.
So is it based on some Pamphilow's models, or it's some other track?
No, it's Oxford Chase. It's software for simulate cardiac electrophysiology, and it's finite element method.
Okay. And do I understand it correctly that it's more or less personalized, right?
Yes, it's personalized simulations. It's personalized based on computed tomography data. I've worked on this publication 5 years from start of my studies in master degree, and currently I finished this publication.
How do you take into account, you know, some, let's say, psychological effects on the ECG in this case? Or
sorry, physiological,
psychological, like, you know, the mood,
no, it's
everything that is happening in our head.
No, it's simulation only one ECG complex. It's not heart rate study. It's study only about one complex.
No, but still, you know,
Can you repeat what program you use when you create a 3D model and use FEM method?
Finite element method, I used Oxford Chase. And currently, if you want to simulate some electrophysiology, it's how it named CARP. Open CARP is more preferable choice for you, because it's simple. It's more simple, and yeah, it's more simple. For creating the models, we use proprietary solutions, but also our group can build our own segmentation with neural networks, and with other methods we have both pipeline with neural networks and without, only with mathematical morphology. Transformation from voxel models to surface mesh happened via from proprietary solution. It's described in articles, or from also we can make it from cube marching algorithms that's implemented in Scikit image and passing results through some scripts on MeshLab. And after this, we join several meshes together, it's surface meshes, and build a complete 3D model with tetragonal mesh using the GMSH.
Okay,
GMesh.
Yeah. Okay, thank you.
Does your model require some maybe special parameters?
We choose reference models, and we have a range of variation for basic physiology. Our models require CT or MRI scans. We need to know precisely the geometry of the cardiac ventricles. And also our model don't include a conduction system in the heart. It's basic idea of our study. We use patient with point activation. And for this reason, it's from one side, it's more simple to simulate. From other side, it's more clear data because we exclude uncertainty that's included in structure of the conduction system in the heart, because real structure of conduction system in heart is not so easy. Some people has anastomosis between left and right bundle branch. Some people has ischemic conditions, and for this reason, some branches don't work really. And it's really very tricky problem. And it's for our point of view, and for my personal point of view, the real problem between for translation of any models in clinics, it's not the computational methods, it's not knowledge about cardiomyocyte physiology. It's problem in cardiac conduction system, because variability between different humans is too high.
And what can you maybe highlight what you haven't done yet that you would improve if you had like one more year to work on this paper?
Sorry, what we will do tomorrow?
No, imagine you had like one more year to do this study on this work. What would you include? What's still missing?
Okay, what's still missing in this study? We used very complex. We used the domain model with bus. It's a very physical, realistic model of human ECG. It's include a lot of scene issues and other stuffs. And for this reason, it's very computationally expensive. One model is compute about 1 day, not really 1 day, but about 12 hours, 1 night. And part of the study is sensitivity analysis, and we use only one at a time approach for sensitivity analysis. It means that we choose some reference parameters of the models and change it in one direction, then change it in other direction, then make it in other direction. And this is bad because if we change it on the corner of this box in parameter space, result may be absolutely different. But this is very difficult to spaces when it's very easy to small spaces, but number of points increased in very fast, and studies of global sensitivity analysis for models with 12 parameters is absolutely terrific tasks. It's very difficult. If I had enough computational power and one more year, I used global sensitivity analysis. It's much better for any models. And I highly recommend if you use models not from statistics, not from machine learning, but you try to write some differential equations or write some algebraic equations for your models. You, in any times, you need to use sensitivity analysis, some sort of sensitivity analysis for found a range of parameters when when your model work correct and provide adequate results. It's very important. And many studies in life science now work on application of sensitivity analysis in this field, in simulation of living systems.
Okay, thank you.
Thank you. I invite your work, your following work, and I hope you show what you do. Okay, we have 1 minute before start. 1 minute. And of course, I close schedule. Okay, and the next block of our perfect conference. Ekaterina Evdokova, recognition of dangerous rhythm disturbances from short ECG fragments.
Yes, it's me.
Let's start.
Okay.
We're ready.
Okay, can you see my presentation?
Yes.
Yeah, okay. Good day, colleagues. My name is Evdokova Ekaterina, and in the next few minutes, I will tell you about my project work, recognition of dangerous rhythm disturbances from short ECG fragments. The purpose of this research is to carry out a binary classification separating dangerous and not dangerous arrhythmias according to the spectral description of the ECG fragments using Fisher-Linear discriminant and the convex Hill classification. The main emphasis is on the use of short EKG ECG signals because we can diagnose the violation as early as possible. The objective solved on my way to the aim are written. It's necessary to reliably identify dangerous arrhythmias at the time of the occurrence. This slide shows methods using for detecting dangerous arrhythmias. It's rather difficult to carry out a comparison of the effectiveness because authors use different database with different content, and it's hard to assess the effectiveness of this algorithm. In addition, the ECG fragments of different duration. This can affect the speed of resuscitation and patient survival. The ECG signals with disturbances have a sharp change spectrum in the frequency domain. That's why we transition to the frequency domain of signal analysis. Recognition of these dangerous violations should occur as fast as possible, I said that. And in this work, we consider a method of convex hills, which is completely original. And we compared the effectiveness of this original algorithm with well-known FLD method. This slide shows the classification of dangerous arrhythmias used in our work. The data were selected manually from a known database. The link to this database is given at the bottom of the slide. Difficult cases were discussed with the doctor. This slide is about FLD method. The meaning of this method was to find the equation of the separating high plane. You can see it in equation number 2, and assign the object to class 1 or to class 2, depending on its position relative to this plane. Fisher criterion is used to find the white vector, and this criterion shown the ratio of spread between classes to the average spread within the classes, and this criterion was maximized. This slide about convex Hill classification, and in this method, it's necessary to determine the convex hills of two classes and assign the test vector to the nearest one. The training set of one class has the form like equation number 1, and then the convex hill generated by this set is defined as equation number 2. It's necessary to define optimal solution and determine whether the test object is located inside or outside the convex hill. We can estimate the proximity of a given point or object to the convex hill of these classes, find the distance from this point to the convex hill D. This slide shows experimental results. This is about FLD method. The object of analysis for each class is ACG fragment with a duration of 2 seconds. For analysis in the frequency domain, we obtain a set of spectral features in the range from 0 to 50 Hertz. The final sample was divided into training and test. Each object was described by 50 spectral features. There was also an addition feature, the total power of the ACG fragment, and the size of the training and test sample is 135 objects of each classes. That means the total size of training set is 270 objects, and the test sample has the same size. All data were normalized by total power. The effectiveness of this method was assessed by the number of correctly recognized objects in the test set. An accuracy matrix was complied, and the sensitivity, specificity, and overall accuracy were calculated for each method. The accuracy matrix for FLD method you can see in the table number 1. An experiment was also carried out on the classification by the FLD method for a complete set with 540 objects. And the classification results you can see in the table 2. Based on these results, we can see that non-dangerous arrhythmia are better detected. Although the sensitivity is more important for solving problem described above, because it's necessary to determine as many true positive objects as possible. This slide about experimental results when we use convex hill classification, and we can see results in the table number 3. We also used leave on out cross validation during the classification experiment for all set, and these results we can see in table number 4. And in conclusion, I want to say that we considered methods and algorithms for binary classification of biomedical signals based on description of the frequency domain. The FLD method and the classification of the convex hill are considered and applied. And this algorithm helped to recognize arrhythmia on short ACG fragments. Timely detection of dangerous violations saves the patient's life through the use of resuscitation measures, primarily such as defibrillation. This is references, and thank you for your attention.
Thank you very much. Maybe some questions from our colleagues. Okay, in this case, I ask you one question. In 2017, will be 2017. There are PhysioNet challenge about classification of short ECG fragments, and this method proposed some neural networks that separate one variants from others, and results was much better than any other solution based on classical approach based on feature extraction and classification. Also, there are some challenges in Chinese when people classify not only short fragments, but short fragments with all 12 leads, and these data sets also available. Why you choose methods that's SVM? It's a classical method for for
Okay.
studies?
I say that convex hills is the original method, and we try to compare results when we get from convex hills methods with FLD methods, because it's well known. It's such as methods which very useful and use. And we want to compare the results.
And where this method is described?
What?
You use original methods. It's convex hulls. It's
Yes. Yes.
okay. And where can I read about this method?
Okay, you can read about this method in I think in our article, and I maybe do references to this method. And I think, yes, I say about this method in article, and some articles exist, and they you can see about this method.
Thank you. Maybe okay, yeah.
I have one question. She used a duration. You used a duration of 2 seconds for the fragments. What is the criteria to use just 2 seconds, and why you didn't use based on the cycle number?
Why we use 2 second duration? Yes. We use this duration because it's short, but it's a duration which allows us to find the spectral description of these signals, ECG signals, and get some results which are with good accuracy.
So, during your study, did you use another duration? You made the comparison, or you used it because like it is standard for you, that or from previous studies of your supervisors? And
we use only 2 second duration because we have the known database, and then we mainly select from this database 2 seconds fragments, and this is big work. That's why we work with only 2 seconds fragments. Yes.
Okay, thank you for your answer.
I think you have mentioned that you didn't use the whole big MAT-big database. You selected some subset of it, right? And what was the criteria?
We have the big database, then we manually select with the doctor some arrhythmias, which which you can see in the second slide, and we then create 2 classes: dangerous arrhythmias and non-dangerous.
Okay.
Okay, thank you very much. And I ask about the second presentation in this block. Ahmed Mahmoud, automatic bioimpedance signal analysis, smoothing process efficiency evaluation, efficiency evaluation in determining the vascular tone type. Sorry. Are you ready?
Yes, I am ready.
Okay, let's start, please.
Good afternoon, everyone. Thank you for having me. My name is Ahmed Hamoud, PhD student in Bama Moscow State Technical University in Department of Medical and Technical Information Technology. And I am going to speak to you today about the automatic bioimpedance signal analysis, smoothing versus efficacy evaluation in determining the vascular tone type. Vascular tone refers to the degree of blood vessel constriction in relation to its full expanded state. The bioimpedance technique can be used to to determine vascular tone type in human lips. This method is considered effective in determining blood vessels tone and many other biomedical issues. There is three types of vascular tone are often encountered: normotonic, hypotonic, and hypertonic. In Figure 1, we see the ideal bioimpedance signal and its basic feature points. C1 is the first systolic wave peak. C2 is the second systolic wave peak. D is a diastolic wave peak. B is a pre-systolic wave peak, and I is the incisor. Type of vascular tone is usually determined by the ratio between two values: dichrotic index DKE and diastolic index DCE. In Figure 2, we see a real bioimpedance signal from the lower part of leg and its basic features points, in which we can determine the dichrotic index and diastolic index C and I and D. And in Figure 3, we can see the areas of vascular tone that detected by DKE and DCE. In circle B, that is the area of hypertone, and circle A and C is the area of normotonic, and circle D is the area of the hypotonic. Problem statement: when applying an algorithm for automatic signal features point detection, it is necessary to determine the method for signal smoothing. Considering that the algorithm work with recorded signals from separated parts of the body with the same general shape, one method can be adopted for smoothing the original signal. In Figure 4, it's the raw signal obtained by Rio-32 device, Rio-32 device from the upper part and lower part of the leg. In the leg D, the lower part of the leg signal of lower part, we can see that all features points is clear, C and I and D. But in the signal leg up, the upper part, just feature point C is clear. In most cases, the point C is clear, while the point I and D is not clear as the signal in leg up. For the methods, many methods can be used for smoothing signal, but the question is which method I had to use and which criteria determine the best method. In our study, we used three methods that is common in signal processing. It's Savitzky-Gulay smoothing and Lewis and binomial smoothing. Figure 5 shows the first stage result of signal smoothing using the three methods. It's clear that we have to reduce the window width for the binomial and Lewis, and we had to increase it for Savitzky-Gulay. In the final stage of smoothing using the three methods for one cycle, Figure 5 shows the results, and we can see that the results of smoothing is acceptable in general. But the most important question: which method I have to use in my algorithm? For discuss this results, the obtained results must be tested in order to have a good and effective discussion about them. The table shows the average time samples numbers of features point, and this numbers is the samples and not real time. The value of average C, average I, and average D express the mean time in which features point C, I, and D respectively have been detected in the cycle. And to make it clearer, in the figure, we can see amplitude and samples. In this table, the average C is the average C time for all cycles in our long-term signals. The tested signals have 520 cycles. For detecting error percentage, the second way to find the error in determining time of feature points C, D, and I is by finding the error percentage. To do that, we get a group of 150 cycles has been selected from the signal at separated time. The features points during these 150 cycles has been manually determined, and then the conversion has been made with each of the used methods. The standard method or way which has been adopted is to reject every cycle with error in feature points time greater than 50 symbols or 0.1 second. And based on this method, among the 150 reference cycles for the Savitsky-Golay method, we found 134 cycles. And similarly, 130 cycles has been matched for the binomial and 100 and same cycles for Lewis. From these results, we can say that Savitsky-Golay and binomial is best for our research, because we found these 3 points in the larger amount of cycles. But how we can judge which method, Savitsky-Golay or binomial, we have to use in our algorithm? The figure figure 6 shows the error in determining time of features point C, D, and I. And we can see that the less error in time of this features point is by binomial method. So, as a conclusion, in this work, the general shape of bioimpedance signal in human limbs and its main features point, which are used in automatic analysis of the signals, has been presented. Several methods of the signal smoothing has been presented as an essential step in signal processing and analysis. According to the obtained results, choice of the methods and its coefficients depends on the study purpose. As an example, Savitsky-Golay method can be used if analysis versus mainly depends on the feature point C, and the binomial smoothing gives more accurate results in the future point time for C and I and D, and as a result for type of vascular tone. Thanks for your attention.
Thank you very much. Anton, maybe questions from you? Oh, yeah.
I'm ready for your questions.
Well, my question will be, maybe sounds strange, but is the smoothing the only way to find these feature points, or there can be some completely different approaches for this task?
Yes, there is another way for find this points. We have 3 ways. First, manually, and that is gives the best result, but because the doctor or scientist he can see it. And second, by algorithm, as our work, and third way is by machine learning. But for machine learning, that is we must have a very big database to do that.
Okay, in MATLAB language and in SciP module in Python, you can find function peak detect CVT. This function uses wavelet smoothing for local window and detect peak and with these windows. Do you try to compare your methods and Savitsky Glide and others with this function because it's most usable function
Yes,
for this task?
As a basic, I use Python, and in SP, yes, there is Savitsky Glide as standard, and I write the binomial method. Our purpose of study, the objective purpose, is how I can compare that results, and by using the smoothing methods in CP, Python, and binomial. The purpose was to find the error percentage in time, and after that I chose binomial, but I tried smoothing methods in Python SP.
Okay, I talk not about smoothing, but not Bayesian smoothing, but about wavelet smoothing. Okay, I copy name of this function in chat. Maybe it help you in further studies. And from my point of view, for this studies, it's very important to compare your approach with some baseline approach, which is widely used in this field. Okay, in any case, thank you for presentation. It's good work. And we go to the next. Do you have any questions? My friends? No questions. Okay. Maybe some questions on YouTube because I don't check it about those about half hour. Okay, the next presentation is Hanadis Soliman. Investigation of the transformation methods accuracy of 12 leads ECG, 2 orthogonal leads using multiple error evaluation metrics. Okay, interesting topics. Let's start, please.
Hello, everyone. My name is Hanadi Sulaiman. I was earlier in the first section. So my study is about investigation of the transformation method accuracy of a 12-lead ECG to orthogonal leads using multiple error evaluation methods. You can hear me?
Yes.
Okay, great. Okay. So, what is the relevance of our work? First of all, we know that the cardiovascular diseases are the leading cause of mortality globally. So while using VLB, we are able to diagnose these disorders. To detect or determine the VLB signals, we can estimate them using the heart vector magnitude. This heart vector magnitude is not obtained clinically, but we can calculate it from orthogonal leads. The orthogonal leads are not anymore used in clinical detection. They are not registered most of the time. So we need to transform the 12-lead ECG to orthogonal lead. So our objective is to investigate the appropriate metrics for the error evaluation of this transformation method from 12-lead ECG to orthogonal leads. We investigated 4 transformation methods: reverse inverse transformation, coarse regressive, BLSV, and QLSV. First, our use database. Our investigation used the PTP diagnostic ECG database. It is a 12 ECG signal with orthogonal leads of a 12-bit resolution and 1 kilohertz sampling frequency. We selected randomly 88 signals out of 549 signals to achieve a margin of error about that is less than 10%, 9.58%, with a confidence level that it is 95. Our selected signals contained one record of patient with dysthymia, one record of healthy, 4 record of healthy, 80 record of myocardial infraction, and 3 records without diagnosis. We took 10 cardiac cycles for this analysis. We filtered each signal, each segments with, first of all, an adaptive cutoff filter to reject the power line noise of 50 Hertz. We used a high pass filter with a half Hertz cutoff frequency to reject the respiration noise. We used low pass filter with a cutoff of 300 Hertz, and we used the wavelet filter to reduce the random noise. So, as we can see in the graphs, we have at first to the left, we have the worst inverse transformation, which is a model-based approach. You can see that the difference between the real and the transformed data is highlighted by the cyan color. We can see that there is a big error here between, especially on the peaks, in the local peaks. Also, we can see on the right part of the screen, we can see that we have, of course, it is a regressive based approach, and also you can see that the error is highlighted by the cyan. For the PLSV transformation, it is also based on regression, but we use the entire B wave to transform. So our basic focus is on the B wave. While QLS is it is also regressive, and we focus on the QRS segment. We can also see in the graphs the errors representation in the vector magnitude, not in the X, Y, Z, the orthogonal legs, but only in the vector magnitude. So our evaluation metrics. We decided to use different evaluation metrics. First of all, we decided to use the continuous that they are used in the previous studies, like mean absolute error and root mean square error. And we decided to investigate the discrete ones. Why? Because the data that we are having is a discrete one. It is just like discrete curves of data that being interpolated when we are when we're drawing it. So we use the 3 measurements: Hausdorff distance that measures the distance between the curves from many points to many points; Fritschet distance that shows the similarity of 2 curves using measuring the distance between the points from one point to another point. Also, we use the 2 sample Kolmosov Smirnov to compare which is used to compare if the 2 curves are from the same distribution. Okay. So our result, as you can see in this table, we can see that the highlighted results, that the one in bold, are the best results. As you can see that course has like the best performance here. We can see that the Hausdorff distance and the Fritschet distance have the same value, which is expected. And for the t-test decision, we can see that for all the transformation method, we have the same value, that it is closer to 0, which means for sure that those curves are not from the same distribution function, because as we know, the ECG has no distribution function. So we saw the errors. What are the reasons of those errors? First, we have the incorrect location of the electrodes. The 12 leads and the orthogonal leads are placed on the body, on the torso of the
patient, the subject, and they may have like we may have a human error in placing them. Second of all, we had each person of us like has a different heart structure, different localization for. So that means that we have different localization for the leads to be put. Third, we have like that the ECG will is influenced by the heart position and the size of the ventricles of the arteria and or the myocardial morphological structure. What is our conclusion? We are expecting error are expected when we use transformation method to convert 12 lead ECG into orthogonal leads. Second of all, the course transformation proved to be to achieve the best performance, the better performance between the based on the metrics that we have. To improve these results, we need to eliminate the errors that by their source. Also, what we can add here, why did we replicate this study? There is also there is other studies that is similar to this. So what is the difference? First of all, the most similar one, it is described in our paper. It is just 50 signals, 50 instances, and only from healthy patients. Also, their graphs, their comparison was based on X, Y, and Z, and not the vector magnitude. So this is the main difference between our approach and their approach. But why did we replicate it? For our database that I already talked about in the previous presentation of mine, we said that it is a database of 12 lead ECG, but without orthogonal leads. So what we need is to exactly, accurately, precisely transform those 12 ECGD to orthogonal. Why do you need that? To compare the characteristics that we will have from the orthogonal leads, the characteristic of the LVLB that we can extract from the orthogonal leads with the one that we will just extract from our 12 lead ECG, the surface one. Also, we need to, at the first step, we compared the transformation methods based on randomly selected signals that, and we can see that we had some, like we had a lot of myocardium infarction states in them. So what we want to do now is to analyze the best two transformation method on a different type of arrhythmia and how if this is effective or not. Also, like as we can see that our base is to investigate the metrics that we can use. So based on our results that we can see here, that we will not anymore use free trade distance or KVS test decision. So we can eliminate those metrics in further studies. This was my presentation. Thank you for your attention. If you have any answers or any questions, I'm ready to answer.
Thank you very much. Questions from our colleagues?
My question will be quite simple. You mentioned that you have used like 88 out of 500 people from this database. Why such weird number?
So as I mentioned, that we are like statistically, you need to use a sample size that will give you less than 10% for a margin of error. So to evaluate that, you have statistical calculation based on the confidence level that you want to have. For us, it was like 95, the highest. So we calculated the number of the samples that we need from the whole database that will
give us less than 10% of like error margin. That's why we didn't use the sample as all. So when you have any statistical problem, you don't use the whole population. You take just one sample of it, and this sample has to be based on some criteria. And the criteria that we read about it was that we have to make it less than 10% for the margin of error. That's why we used 88.
Okay, thank you.
Thank you very much. Thank you for your presentation. Currently, I'm asked to start the last speaker today, Ekaterina Drožennikova, development of an instrumentation amplifier for radiographic measurements.
Good afternoon. Today I want to tell you about development of an instrumentation amplifier for radiographic measurements. Nowadays, cardiovascular diseases are standing in the first place due to the death in Russia. But 80% of paralytic infarcts and strokes could be prevented. Determining parameters of the severity and type of cardiovascular diseases will help to reduce the death rate. Impedance cardiography is a non-invasive method based on the registration of changes in bioelectric resistance arising as a result of pulse blood filling. The measurement method is consisted of applying a low amplitude alternating current with frequency 100,000 hertz through the area of interest and measuring alternating voltage. Alternating voltage consists of electrocardiographic signal, polarization voltage, and radiographic signal. The radiographic signal is the sum of a weak differential signal and large common mode noise, which occurs not only at a mains frequency of 50 Hz, but also at a probing current frequency. The amplitudes of biopotentials are tens of millivolt, and biological impedance is a complex quantity, and the reactive component of which is an order of magnitude less than active component. To register small changes in the signal, it is necessary to increase the accuracy of recording biological potentials to reduce the noise of the hardware at the stage of amplifying the differential signal. Here you can see the typical structure of a radiographic device. And the main component of a radiographic device at the stage of primary conversion of biosignals is an instrumentation amplifier. The design quality of which determines the main metrological characteristics, the efficiency of the diagnostics, as well as the technical parameters of the diagnostic equipment created on the basis. The instrumentation amplifier removes most of the common mode noise at the input before amplifying the signal. And the differential signal transmission allows information to be transmitted with the lower voltages of the diagnostic equipment created low voltages, good signal to noise ratio, and higher data rates. Typical instrumentation amplifiers are created on the basis of operational amplifiers, and here you can see requirements for choosing operational amplifier. The radiographic devices have some special requirements because it is necessary to have common mode rejection ratio more than 113 decibel at the frequency of 100 kilohertz. And as the current must pass through the biological object and not through the input stage, the operational amplifiers included in the instrumentational amplifier must have low input currents, less than 20 picoamperes. And of course, for of course, we must reject noise, and in operational amplifiers must have low noise voltage density, less than 10 nanovolts per hertz root. In this work, I compared three most known structures of instrumentation amplifier. On the slide, you can see a classic instrumentation amplifier on 3 operational amplifiers. To have a differential signal, we use one instrumentation amplifier for each pin. On the slide, you can see equation for calculating resistance of resistor of a generated gain resistor. But the main disadvantage of this scheme is a separate amplification of signals. On the second scheme is instrumentation amplifier with cross connection. It is based on the classic scheme, but the regulated resistor is connected. There is one regulated resistor, and it is connected to amplifiers. For this. This scheme has some disadvantages with the excuse me.
Yes, thoughts. Something wrong?
No. As you can see on this scheme, for this regulated resistor, the gain is positive. And there is another place of regulated resistor to another pins if we need negative gain. And the third architecture is instrumentation amplifier with inverting amplifier. The inverting amplifier is connected in the second stage of instrumentation amplifier, and the positive output is the typical output of instrumentation amplifier, and the negative output is output from the inverting amplifier. The calculation of resistance of regulated resistor is same as for classic architecture. All circuits were modeled in the open access program LTSpice by analog devices, and we calculated RMS noise voltage on the range from 1 Hz to 1 megahertz. On the graph, you can see that the best results are from the third circuit, and it's because of the low because of a lower number of operation amplifiers. In conclusion, I want to say that the best results were shown by the third circuit in instrumentation amplifier with inversion amplifier, but these results, the shown results, are results which we can achieve. And we must note that errors in the PCB routing can enhance noise, and the noise voltage will be bigger. Thank you for your attention. That's all. I can answer your questions.
Okay, thank you very much. I want to ask you about application of this device. Do you try it not in measurements of basic properties, but in real circuit and how it work with real circuit? Maybe we make some prototypes and test it on some data.
There is no prototypes yet, but the main reason of modeling this scheme is that biological impedance is complex quantity, and we want to measure reactive component and active component of bioimpedance separately. To calculate the phase of a radiographic signal of biological impedance, and it can have some information about diseases and about diagnostics.
Okay, thank you. Any other questions, please? We have not enough competence here for ask proper questions. Okay, thank you very much. It was the lightest presentation, and currently we are free and we can discuss something. Discuss first day, first section, discuss best ideas, best presentation. Yeah. Ekaterina, we can turn off your screen. It's not so important now. Dear friends, I thank you for coming to our conference, for participation first day of conference. I'm glad to see a lot of good presentations. Yeah, thank you very much. In this case, YouTube look at my face and not on the presentation. We glad to see you here, and we glad and we will very happy if you join us to the following day and ask you questions, found new ideas. I help as much as I can to some people. So I sent some reviews, some links, and some discussions about several technologies. We can open chat in Zoom and look. That's the really big discussion. And I hope you can, if you already registered in system, you can open any presentation and any paper, any conference paper in preprint form that will be sent in this conference, and use this knowledge to find new contacts, new collaboration, new ideas, and other. Thank you very much. Have a good day, and we will invite you tomorrow.
Thank you, Konstantin, for hosting this subsection.
Thank you too for choosing me as co-chair.